Welcome friends, I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you've found the right place. Before we begin, I'd love to know where in the world are you listening from. Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the ancient dance between Mars and its cosmic visitors. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who have already joined along, thank you. In the cold vacuum beyond Mars's orbit, two ancient wanderers drift through space with the patient inevitability of geological time. The twin asteroids known as 3I Atlas carry within their frozen cores the memory of the solar system's birth, ice and rock that condensed from primordial gas clouds 4.5 billion years ago. Their surfaces, dark as charcoal and pocked with the scars of countless micrometeorite impacts, catch the faint light of distant stars as they tumble slowly end over end through the cosmic void. These are not ordinary asteroids. Born in the frigid outer reaches of the solar system, they harbour water ice in quantities that dwarf Earth's polar ice caps, locked away in crystalline lattices that have remained unchanged since before life first stirred in terrestrial oceans. Scientists classify them as interstellar visitors, though their true origin remains wrapped in the mystery of deep space and deeper time. Each asteroid measures roughly 2 kilometers across, their irregular shapes carved by billions of years of cosmic erosion, their surfaces as black as the space between stars. The ice within them exists in forms unknown on Earth's surface. Here, water molecules arrange themselves in exotic crystalline structures that can only form under the extreme cold and pressure of deep space. Some ice exists as clathrate hydrates, water molecules forming cage-like structures around trapped methane and carbon dioxide. Other regions contain pure water ice so ancient it predates the formation of the terrestrial planets, crystallized when the solar nebula was still collapsing under its own gravity. Mars turns beneath them, a rust-coloured sphere suspended in the cosmic dark, its thin atmosphere barely visible as a gossamer thread against the starfield. The planet rotates with metronomic precision, completing one full rotation every 24 hours and 37 minutes. A rhythm that has persisted for billions of years with only the slightest variations. Its two small moons, Phobos and Deimos, trace their own elliptical paths around the planet like faithful attendants, their surfaces as cratered and ancient as the asteroids that now approach from the outer darkness. The planet's weak gravitational field tugs gently at the passing asteroids, altering their trajectories by degrees so subtle that only the most sensitive instruments can measure the change. This gravitational influence extends far beyond Mars's visible disk, reaching out through space like invisible fingers to caress anything that ventures too close. The asteroids feel this pull as a whisper of acceleration, their orbital velocities increasing by mere centimeters per second as they fall toward their inevitable rendezvous with the red planet. It is a conversation conducted in the language of orbital mechanics, played out over distances that reduce mountains to dust motes and years to heartbeats. The laws of physics govern every aspect of this celestial ballet, from the precise curves of the asteroid's approach, trajectories to the exact moment when gravitational capture will become inevitable. Newton's equations describe their motion with mathematical poetry, each variable representing forces that have shaped the cosmos since the first stars began to shine. The red planet waits, as it has waited for eons, patient in its solitude. Its surface bears the scars of 4 billion years of cosmic bombardment, from the massive impact basins of the early heavy bombardment to the countless smaller craters that pepper its ancient terrain. Only took 4 billion years to perfect this particular shade of rust, the result of iron oxides coating nearly every grain of dust on the planet's surface. The Martian regolith contains enough iron oxide to colour the entire planet in shades ranging from deep burgundy to pale salmon. Depending on the angle of sunlight and the thickness of the atmosphere, Mars's atmosphere hangs around the planet like a threadbare blanket, composed primarily of carbon dioxide with trace amounts of nitrogen, argon, and water vapour. The atmospheric pressure at the surface equals roughly 1% of Earth's sea level pressure, so thin that liquid water cannot exist except under the most favourable conditions. Yet this tenuous envelope of gas still manages to support weather patterns, dust storms that can engulf the entire planet, and seasonal changes that cause the polar ice caps to advance and retreat with clockwork regularity. The planet's magnetic field, such as it is, exists only in scattered remnants embedded in the ancient crust. These magnetic anomalies tell the story of a world that once possessed a global magnetic field like Earth's, generated by convection currents in a molten core. But Mars cooled more quickly than its larger neighbour, and the dynamo that once protected it from solar radiation fell silent billions of years ago. Now the planet stands naked before the solar wind, its atmosphere slowly bleeding away into space grain by grain, molecule by molecule. The asteroids approach with the unhurried certainty of celestial clockwork, their frozen cargo destined for delivery to a world that has been thirsty since its atmosphere first thinned to whispers. Deep within their cores, ice that has never known warmth waits to transform, to sublime directly from solid to vapour in the violence of impact. This ice carries within its crystal structure the chemical signature of the early solar system, isotopic ratios that tell stories of stellar nucleosynthesis and the formation of the first solid matter in the cooling nebula. In the silence between worlds, ice remembers its purpose. It remembers the time before planets, when the solar system was nothing but a disk of gas and dust surrounding a young star. It remembers the slow accretion of the first planetesimals, the gravitational dance that swept the inner solar system clean of volatiles and concentrated them in the cold outer regions. It remembers crossing the frost line, that invisible boundary beyond which water could first condense into solid form. And it remembers the patient accumulation that built these ancient visitors grain by grain. The distance between the asteroids and Mars shrinks with each passing moment, measured now in millions of kilometres but decreasing steadily as gravity's inexorable pull draws them closer. Soon, the red planet's disk will begin to show detail to any observer riding along with these cosmic messengers. The Great Canyon system of Valles Marineris will become visible as a dark scar across the planet's face, and the towering volcanic peaks of the Tharsis region will rise above the curve of the horizon like sleeping giants. The solar wind streams past Mars in an endless river of charged particles, carrying with it the breath of the sun at velocities that dwarf the fastest hurricanes ever recorded on Earth. These subatomic messengers, protons, electrons, and heavier ions flow outward from the solar corona at speeds approaching 400 kilometers per second, painting invisible auroras in the thin Martian atmosphere when they interact with the planet's patchy magnetic field remnants. The wind carries more than particles. It carries magnetic field lines twisted and braided by the sun's rotation, creating a complex web of electromagnetic forces that extends throughout the solar system. Mars orbits within this solar wind like a small island in a cosmic stream, its weak gravitational field barely able to hold on to its tenuous atmosphere against the constant pressure of stellar radiation. The planet's orbital mechanics follow Kepler's laws with clockwork precision, tracing an elliptical path around the Sun that varies in distance from 206 million kilometers at perihelion to 249 million kilometers at aphelion. This orbital eccentricity means that Martian seasons vary dramatically in length and intensity, with southern hemisphere summers coinciding with the planet's closest approach to the Sun. The approaching asteroids follow their own orbital paths, trajectories that were set in motion billions of years ago by gravitational perturbations in the outer solar system. Their current course represents the culmination of countless tiny influences, the gravitational tugs of Jupiter and Saturn, the pressure of solar radiation on their dark surfaces, and the subtle recoil from sublimating ice as they passed closer to the Sun during previous encounters. Each force has contributed to their present trajectory with mathematical precision, creating a path that will intersect Mars's position in space at exactly the right moment. Orbital mechanics operates on principles that seem almost magical in their elegance. The same equations that describe a thrown baseball also govern the motion of planets and asteroids. Scaled up to cosmic proportions where velocities are measured in kilometers per second and distances span millions of kilometers, the asteroids currently travel at roughly 18 kilometers per second relative to the Sun, their kinetic energy representing the accumulated gravitational potential they have gained during their long fall toward the inner solar system. As the distance to Mars decreases, the planet's gravitational influence begins to dominate the asteroid's motion more strongly. What began as a barely perceptible tug now becomes a steady acceleration, bending their trajectories from nearly straight lines into gentle curves that will eventually become hyperbolic arcs around the planet. The mathematics of orbital mechanics dictate that these visitors cannot be permanently captured by Mars's weak gravity. Their approach velocity is too high, their kinetic energy too great to be completely absorbed by gravitational binding. The red planet continues its rotation beneath the approaching visitors, each 24-hour, 37-minute day bringing new regions of the surface into view. Ancient impact craters rotate past like geological timepieces, their circular rims and central peaks telling stories of cosmic collisions stretching back billions of years. The largest of these impact structures, like the Hellas Basin, measure over 2,000 kilometers across, scars left by asteroids so massive they temporarily melted portions of the Martian crust and threw debris completely around the planet. Mars's two small moons maintain their own orbital dance around the planet. Phobos racing around Mars in just 7.5 hours, while Deimos takes 30 hours to complete one orbit. These irregularly shaped satellites are likely captured asteroids themselves, their dark surfaces composed of carbon-rich materials similar to the most primitive meteorites found on Earth. Phobos orbits so close to Mars that tidal forces are slowly pulling it apart. In roughly 50 million years, it will either crash into the planet or break up into a ring system. The approaching asteroids carry within their frozen cores isotopic signatures that reveal their origins in the outer solar system's primordial disk. Their ice contains deuterium ratios that match measurements from comets and other Kuiper belt objects, confirming their birth in the cold regions beyond Neptune's orbit. This heavy water with hydrogen atoms containing an extra neutron formed in the frigid depths of interstellar space before the solar system even existed, preserved in ice that has remained unchanged for over 4 billion years. Scientists puzzle over the exact mechanisms that send such objects on collision courses with inner planets. The gravitational influence of the giant planets can perturb objects in the outer solar system, sending them on long, elliptical orbits that eventually bring them close to the Sun. Some may originate from the scattered disk beyond Neptune, while others might come from the even more distant Oort cloud, a spherical shell of icy bodies that surrounds the solar system at distances measured in thousands of astronomical units. The mystery deepens when considering the timing of such impacts. Why now? After billions of years of relative quiet, should Mars receive visitors from the outer darkness? The solar system's architecture has remained relatively stable since the late heavy bombardment ended nearly 4 billion years ago. Yet gravitational resonances and chaotic dynamics ensure that objects continue to migrate between different regions of the solar system over geological timescales. Only took 4 billion years for these particular wanderers to find their way to Mars, practically instantaneous in cosmic terms, yet longer than life has existed on Earth. The orbital mechanics of the approaching encounter involve three-body dynamics of staggering complexity. Mars, the asteroids, and the Sun all influence each other gravitationally, creating a system of equations that cannot be solved analytically, but must be computed numerically using the most powerful supercomputers. Small changes in initial conditions can lead to dramatically different outcomes, a sensitivity that makes long-term predictions of asteroid trajectories one of the most challenging problems in celestial mechanics. As the asteroids draw closer, their ice begins to respond to increased solar heating. Even at Mars's distance from the Sun, temperatures can rise high enough on sun-facing surfaces to sublimate water ice directly into vapor. This process creates a tenuous atmosphere around each asteroid, a thin envelope of water vapor and dust that streams away from the Sun like a microscopic comet tail. The escaping gas carries with it tiny particles of dust and organic compounds, materials that have remained frozen since the solar system's formation. The solar wind continues its relentless flow past Mars, carrying away wisps of the planet's atmosphere and now beginning to interact with the gas clouds surrounding the approaching asteroids. This interaction creates complex electromagnetic phenomena as charged particles in the solar wind encounter neutral gas molecules, exciting them to higher energy states that eventually decay by emitting photons. The result is a faint glow around each asteroid, visible only to the most sensitive instruments but marking their passage through space with subtle auroras. Time flows differently at planetary scales, where events that seem rapid from a human perspective unfold with the stately pace of orbital mechanics. The final approach phase, which will bring the asteroids from their current distance to impact, will take several more hours, time enough for Mars to rotate through nearly a complete day-night cycle, time enough for the solar wind to carry away another thin layer of the planet's atmosphere, time enough for the cosmic dance to reach its inevitable conclusion. The Martian atmosphere extends upward from the planet's surface in layered shells of increasingly thin gas, each altitude marking a different regime of atmospheric physics and chemistry. The troposphere hugs close to the surface, rarely extending more than 10 kilometers high, while the thermosphere reaches out nearly 200 kilometers before finally yielding to the vacuum of space. Between these extremes lies the mesosphere, a realm of ice crystal clouds and complex photochemical reactions driven by ultraviolet radiation from the Sun. At an altitude of roughly 100 kilometers above the Martian surface, the first asteroid encounters the outermost wisps of planetary atmosphere. Here, gas molecules exist in such low concentrations that they rarely collide with one another, creating conditions more akin to laboratory vacuum chambers than the dense air of planetary surfaces. Yet even these tenuous molecules carry enough mass to begin the process of atmospheric entry, their collision with the asteroid's leading surface generating the first faint traces of heat and ionization. The asteroid plunges deeper into the atmospheric envelope at a velocity of 22 kilometers per second, its kinetic energy so immense that each collision with an atmospheric molecule releases temperatures hot enough to vaporize rock. The leading edge of the asteroid begins to glow with incandescent heat as atmospheric drag converts orbital motion into thermal energy with ruthless efficiency. This process follows the fundamental laws of thermodynamics. Energy cannot be created or destroyed, only transformed from one form to another. As the asteroid descends through progressively denser atmospheric layers, the rate of molecular collisions increases exponentially. What began as isolated impacts with individual gas molecules becomes a continuous hammering by an ever-thickening wall of atmospheric particles. The front surface of the asteroid heats to temperatures exceeding 5,000 degrees Celsius, hot enough to dissociate atmospheric carbon dioxide into its component atoms and strip electrons from their nuclei to create a plasma sheath around the incoming object. This plasma formation represents one of nature's most spectacular light shows, though one played out in wavelengths largely invisible to human eyes. The superheated gas glows primarily in ultraviolet and infrared frequencies, with only a fraction of its energy released as visible light. Spectroscopic analysis of similar events has revealed the characteristic emission lines of ionized carbon, oxygen, nitrogen, and trace metals, each element contributing its own signature to the electromagnetic symphony of atmospheric entry. The asteroid's ice begins to sublimate rapidly as surface temperatures soar beyond the triple point of water. Ancient ice that has remained frozen for billions of years transforms directly from solid to vapor in mere seconds. The phase transition releasing stored latent heat and adding water vapor to the plasma trail streaming behind the incoming object. This water vapor carries within its molecular structure isotopic ratios that differ subtly from terrestrial water. Deuterium concentrations that reveal its origins in the cold outer regions of the solar system. Mars watches this cosmic fireworks display with electronic eyes scattered across its surface and in orbit around the planet. Seismic monitoring stations detect the acoustic waves generated by the asteroid's supersonic passage through the atmosphere. Pressure variations that race across the planet's surface at the speed of sound in the thin Martian air. Orbital spacecraft train their instruments on the entry trajectory, recording spectral data that will later reveal the asteroid's composition and internal structure. The plasma trail extends for hundreds of kilometers behind the asteroid, a luminous ribbon of ionized gas that marks its passage through the upper atmosphere like a cosmic contrail. This trail interacts with Mars's weak magnetic field remnants, generating radio emissions across a wide frequency spectrum as charged particles spiral along magnetic field lines. The phenomenon creates temporary auroral displays in the Martian sky, ghostly curtains of light that dance across the star-filled darkness of the planet's thin atmosphere. Atmospheric entry physics operates according to principles that scale from microscopic molecular collisions to macroscopic fluid dynamics. The asteroid's passage creates a bow shock wave in the surrounding air, a pressure discontinuity that propagates outward at supersonic velocities. Behind this shock front, atmospheric gas reaches temperatures and pressures that temporarily recreate conditions found deep within stellar cores, where nuclear fusion reactions convert hydrogen into heavier elements. The mystery of atmospheric entry lies in the precise mechanisms by which kinetic energy transforms into heat, light, and sound. While the overall energy budget follows conservation laws, the detailed processes involve complex interactions between electromagnetic fields, plasma dynamics, and thermochemical reactions. Computer simulations require massive computational resources to model even simplified versions of these phenomena, and many aspects of high-velocity atmospheric entry remain poorly understood despite decades of research. The second asteroid follows closely behind its twin, tracing a parallel trajectory through the same atmospheric layers. Its entry creates a similar plasma trail, though subtle differences in composition and approach angle produce variations in the spectral emissions and shockwave patterns. The two plasma trails interact electromagnetically, their charged particle streams creating complex magnetic field configurations that influence the propagation of radio waves and the formation of auroral displays. Only took 4 billion years for this ice to return to vapor, a phase transition that reverses the original condensation process that occurred during the solar system's formation. The sublimating water molecules carry within them the memory of primordial nebular conditions, isotopic signatures that preserve information about stellar nucleosynthesis processes that occurred before the sun was born. This ancient water briefly rejoins the Martian hydrological cycle, adding precious molecules to an atmosphere that has been steadily losing water to space for billions of years. The plasma sheath surrounding each asteroid reaches peak temperatures as they descend through the densest atmospheric layers, roughly 20 to 30 kilometers above the Martian surface. At these altitudes, atmospheric pressure approaches 1% of Earth's sea level value, still thin by terrestrial standards but dense enough to create significant drag forces on the incoming objects. The aerodynamic forces begin to stress the asteroid's internal structure, pressure waves propagating through their rocky cores as atmospheric drag creates differential forces across their irregular surfaces. Deep within each asteroid, ice that has remained pristine since the solar system's formation begins to feel the effects of surface heating. Heat conduction through rock proceeds slowly, but the intense temperatures generated by atmospheric entry gradually penetrate inward, creating thermal gradients that stress the crystalline structure of ancient ice. Some of this ice exists in exotic high-pressure phases that are unstable under normal conditions, forms of water ice that can only exist in the extreme cold and pressure of deep space. The electromagnetic effects of plasma formation extend far beyond the visible trail behind each asteroid. The ionized gas creates a temporary disruption in Mars's already weak magnetosphere, altering the paths of charged particles in the solar wind and creating radio blackout conditions in certain frequency bands. These electromagnetic disturbances propagate through the Martian ionosphere at the speed of light, creating transient changes in radio propagation characteristics that will persist for hours after the asteroids complete their atmospheric passage. The Martian surface rises to meet the incoming asteroids like an ancient manuscript written in stone and dust, each geological feature recording chapters of planetary history that span billions of years. Below the plasma trails now streaking across the salmon-coloured sky lies terrain that has witnessed the formation and erosion of continents, the rise and fall of massive volcanic systems, and the slow retreat of an atmosphere that once supported liquid water on the planet's surface. The impact sites wait in patient silence, their coordinates fixed by orbital mechanics and gravitational forces that have guided these cosmic visitors across interplanetary space. The first asteroid targets a region of ancient highland terrain in the planet's southern hemisphere, an area of heavily cratered landscape that dates back to the earliest epochs of Martian history. Here, the bedrock consists primarily of basaltic composition, overlain by billions of years of accumulated dust and debris from countless smaller impacts. The rock layers beneath the surface preserve a geological record stretching back nearly 4 billion years to a time when Mars possessed a thicker atmosphere and surface conditions that might have supported liquid water. Impact crater formation follows physical principles that remain constant whether the impactor measures micrometers or kilometers across. The process begins with contact and compression as the asteroid's leading edge encounters solid rock, at velocities that compress both materials to densities exceeding those found in the Earth's core. During these first microseconds of impact, pressures reach millions of times atmospheric pressure, while temperatures soar to tens of thousands of degrees, creating conditions that instantaneously vaporize both the impactor and the target rock. The shock waves generated by initial contact propagate outward through the bedrock at velocities approaching the speed of sound in crystalline rock, roughly 6 kilometers per second in basaltic materials. These pressure waves carry enough energy to fracture molecular bonds and rearrange crystal structures, transforming ordinary minerals into high-pressure phases that can only form under extreme conditions. Quartz grains become coesite or stishovite, dense polymorphs that serve as diagnostic indicators of impact processes in terrestrial crater studies. As the shock waves expand outward from the point of impact, they excavate material from the growing crater through a process that operates according to scaling laws derived from fluid dynamics. Despite the solid nature of rock, the extreme pressures and temperatures generated during impact cause geological materials to behave like viscous fluids, flowing and deforming in ways that would be impossible under normal conditions. The excavation process carves out a transient crater whose diameter depends on the impactor's size, velocity, and composition according to mathematical relationships that have been calibrated through decades of laboratory experiments and computer simulations. The ancient Martian bedrock yields to cosmic collision with a violence that seems almost deliberate in its thoroughness. Rock layers that took millions of years to form disappear in seconds, vaporized by temperatures that briefly rival those found in stellar cores. The excavation process lifts countless tons of material from depths of several kilometers, hurling this debris high into the thin Martian atmosphere where it will eventually rain back down across hundreds of square kilometers of surrounding terrain. Deep beneath the impact site, geological formations that have remained undisturbed for billions of years suddenly experience pressures and temperatures that alter their fundamental structure. Ancient sedimentary layers become metamorphic rocks in milliseconds, their original textures and compositions transformed beyond recognition by the passage of shock waves. Some materials undergo complete phase transitions, with ordinary silicate minerals converting to dense, high-pressure forms that preserve evidence of the impact event in their crystal structures. The mystery of impact crater formation lies partly in the complex interactions between multiple shock waves as they reflect off boundaries between different rock types and propagate back toward the surface. These reflected waves can actually enhance the excavation process, lifting additional material from the crater floor and walls through a phenomenon known as spallation. The timing and geometry of these wave interactions determine many characteristics of the final crater structure, including the formation of central peaks and terraced walls in larger craters. The second asteroid strikes a different type of terrain roughly 50 kilometers away, impacting younger volcanic plains that formed during Mars's more geologically active period several billion years ago. Here, the bedrock consists of layered basaltic flows interbedded with wind-blown sediments and impact debris from earlier bombardment events. The subsurface geology includes ancient lava tubes and caverns carved by flowing molten rock, voids that will collapse catastrophically when the shock waves reach them. Both impact sites represent the culmination of gravitational processes that began with the formation of the solar system itself. The kinetic energy now being released in these cosmic collisions originated as gravitational potential energy in the original solar nebula, energy that was converted to orbital motion as planetesimals accreted from dust and gas. Only took 4 billion years to complete this energy transfer from nebula collapse to surface impact to transaction, conducted entirely through the patient accounting of celestial mechanics. The impact process generates seismic waves that propagate through Mars's interior structure, carrying information about the planet's internal composition and density distribution. These waves travel at different velocities through different materials, allowing seismologists to map the boundaries between the Martian crust, mantle, and core using the same techniques employed to study Earth's interior. The impacts serve as controlled seismic sources, providing data that will improve understanding of Martian geology for decades to come. Crater formation on Mars differs subtly from similar processes on other worlds due to the planet's unique environmental conditions. The thin atmosphere provides minimal resistance to ejecta travelling at high velocities, allowing impact debris to travel much farther from crater sites than would be possible on Earth. Conversely, the lower surface gravity reduces the velocities achieved by excavated material, creating different scaling relationships for crater size and ejecta distribution patterns. The excavation process uncovers geological materials that have been buried beneath the surface for billions of years, exposing them to surface conditions for the first time since Mars's early history. Some of these materials may contain mineralogical evidence of ancient hydrothermal systems or even biosignatures from the planet's potentially habitable past. The impacts thus serve as natural drilling operations, providing access to subsurface materials that would otherwise remain forever hidden beneath layers of accumulated dust and debris. As the transient craters reach their maximum dimensions, gravitational forces begin to modify their initial bowl-like shapes through processes that operate on timescales of minutes rather than microseconds. The crater walls, unstable under Martian gravity, begin to slump inward while the fractured crater floors rebound upward as the compressed bedrock attempts to return to its original density. These modification processes will continue for hours or days after the initial impact, gradually transforming the fresh craters into their final stable configurations. The violence of impact excavation releases clouds of pulverized rock and vaporized material into the thin Martian atmosphere, creating temporary local weather systems driven by the thermal energy of the collisions. These impact-generated dust clouds will eventually settle back to the surface, but not before being dispersed by atmospheric winds across vast areas of the planet. The finest particles may remain suspended in the atmosphere for months, contributing to the global dust loading that gives Mars its characteristic rusty appearance from space. Within the cores of the twin asteroids, water ice that has remained frozen since the dawn of the solar system begins its final transformation. The extreme temperatures generated by atmospheric entry and impact penetrate inward through layers of rock and metal, reaching ice deposits that have never experienced warmth above absolute zero. These ancient reservoirs of water exist in crystalline forms unknown on Earth's surface, hexagonal ice, mixed with exotic high-pressure phases that can only maintain their structure in the cold vacuum of deep space. As heat flows inward, these pristine ice formations begin to destabilize, their ordered molecular lattices breaking apart as thermal energy, overwhelms the hydrogen bonds that have held them together for billions of years. The sublimation process occurs with startling rapidity once temperatures exceed the triple point of water under the low-pressure conditions within the asteroid's fractured interiors. Unlike the familiar melting and evaporation sequence observed in terrestrial water, this ice transitions directly from solid to vapor without passing through a liquid phase. The phase change releases enormous quantities of latent heat, roughly 8 million joules per kilogram energy, that was originally absorbed when this water first condensed from gas in the frigid outer reaches of the primordial solar nebula. Steam erupts from countless fractures opened by the impact shock waves, carrying with it trace gases that have been trapped within the ice matrix for eons. Methane molecules, carbon monoxide, and various sulfur compounds emerge from their icy prisons like geological memories suddenly awakened. These volatiles represent samples of the original solar nebula's composition, preserving chemical ratios and isotopic signatures from a time before planets existed. Their release adds complexity to the expanding vapor clouds, creating a rich mixture of gases that will briefly enrich Mars's tenuous atmosphere. The expanding water vapor carries kinetic energy proportional to its temperature, creating internal pressure that fractures the asteroids from within as sublimation proceeds. This process resembles the explosive decompression that occurs when frozen carbon dioxide sublimes on Mars's polar caps each spring, but at temperatures and pressures far exceeding anything observed in normal planetary processes. The vapor pressure generated by sublimating ice approaches conditions found in industrial steam boilers, creating forces capable of shattering rock and ejecting fragments at high velocities. Mars's atmosphere receives this gift of water vapor with the same patient acceptance it has shown for billions of years of slow atmospheric loss. The thin envelope of gas surrounding the planet contains roughly 0.3% water vapor under normal conditions, a concentration so low that the relative humidity never exceeds a few percent even during the most favorable circumstances. The sudden addition of thousands of tons of water vapor from the sublimating asteroid ice represents a temporary but significant increase in atmospheric moisture content, particularly in the vicinity of the impact sites. The newly liberated water molecules begin their integration into the Martian hydrological cycle immediately upon release. Some vapor condenses onto dust particles suspended in the atmosphere, forming ice crystal clouds at altitudes where temperatures drop below the frost point. These clouds contribute to the complex atmospheric dynamics that drive Martian weather patterns, providing condensation nuclei that influence precipitation processes and radiative heat transfer through the thin atmosphere. Atmospheric scientists study water vapor transport on Mars using sophisticated computer models that track individual molecules as they move through three-dimensional wind patterns. The planet's low atmospheric pressure and temperature create conditions where water vapor can exist only within narrow ranges of altitude and season. Most atmospheric water vapor originates from sublimation of polar ice caps during summer months, creating seasonal variations that transport moisture from polar regions toward the equator through complex atmospheric circulation patterns. The isotopic composition of the newly released water vapor tells a story that spans the history of the solar system itself. Deuterium to hydrogen ratios in this ancient ice differ measurably from those found in Martian polar ice or atmospheric water vapor, reflecting the different conditions under which it originally condensed. This heavy water formed in the cold outer regions of the solar nebula, where lower temperatures favored the incorporation of deuterium into water molecules. The isotopic signature serves as a fingerprint that identifies the water's origins beyond the asteroid belt. The mystery of water transport in the early solar system remains one of planetary science's most intriguing puzzles. How did water-rich materials from the outer solar system find their way to the inner planets, including early Earth and Mars? The current impacts provide a small-scale demonstration of one possible mechanism: gravitational perturbations that send ice-rich objects on long journeys from their birthplaces to eventual collision with terrestrial worlds. Only took 4 billion years for this particular delivery system to complete its mission, demonstrating the patient persistence of cosmic water transport processes. The sublimation process creates temperature gradients within the asteroids that drive convective flow patterns in the escaping vapor. Hot gases rise from deep within the objects while cooler vapor near the surface sinks, creating circulation cells that enhance heat transfer and accelerate the sublimation process. These convective patterns operate according to the same fluid dynamics principles that drive atmospheric circulation on planets, scaled down to the dimensions of the asteroid's internal cavities and fracture systems. As water vapor escapes from the asteroid's interiors, it carries with it microscopic particles of dust and organic compounds that have been frozen into the ice matrix. These particles include complex organic molecules, amino acids, nucleotide bases, and other carbon-rich compounds that form spontaneously in the cold chemistry of interstellar space. Their release into the Martian atmosphere represents a form of cosmic seeding, delivering prebiotic molecules that could theoretically contribute to chemical evolution processes if suitable conditions exist. The vapor pressure generated by sublimating ice varies dramatically with temperature according to the Clausius-Clapeyron equation, an exponential relationship that means small temperature increases produce large increases in vapor pressure. This sensitive dependence on temperature creates feedback mechanisms that can accelerate the sublimation process once it begins. Heat released by sublimation warms surrounding ice, increasing its sublimation rate, which releases more heat, creating a positive feedback loop that rapidly depletes the asteroid's frozen reservoirs. Spectroscopic analysis of the escaping vapor reveals absorption and emission lines characteristic of water molecules in various excitation states. The extreme temperatures created by impact heating populate high-energy rotational and vibrational modes that are rarely observed under normal planetary conditions. These excited molecules emit infrared radiation at specific wavelengths, creating spectral signatures that can be detected by sensitive instruments on orbiting spacecraft and surface-based observatories. The sublimation process gradually transforms the asteroids from ice-rich objects into collections of rocky debris held together primarily by gravitational forces and impact-generated fracture networks. What began as coherent bodies with significant internal ice content becomes rubble piles with greatly reduced structural integrity. This transformation demonstrates the ephemeral nature of ice in the inner solar system, where even objects that have survived billions of years in the cold outer regions can be completely altered by brief exposure to higher temperatures. Water vapor molecules released during sublimation possess kinetic energies that allow some fraction to achieve escape velocity from Mars's weak gravitational field. This process contributes to the planet's ongoing atmospheric loss, though at rates much lower than the escape of lighter gases like hydrogen. The newly added water vapor will gradually be dissociated by ultraviolet radiation in the upper atmosphere, with the resulting hydrogen atoms eventually escaping to space while oxygen atoms become incorporated into surface minerals through oxidation reactions. The impact explosion sends shock waves rippling through the Martian atmosphere like stones cast into a still pond. But these are pressure waves that carry the energy of millions of tons of TNT released in microseconds. The sudden displacement of air creates compression waves that race outward from both impact sites at supersonic velocities, their passage marked by temperature spikes and pressure variations that dwarf the most powerful storms ever recorded on the Red Planet. These atmospheric disturbances propagate through the thin air with mathematical precision, following acoustic principles that remain constant whether applied to whispers in terrestrial air or cosmic explosions in alien atmospheres. The energy released by the impacts heats vast volumes of atmospheric gas to temperatures exceeding 1000 degrees Celsius, creating thermal updrafts that rise through the stratosphere like invisible pillars of superheated air. These rising columns of hot gas carry with them countless particles of pulverized rock and vaporized asteroid material, lifting debris to altitudes normally occupied only by the highest ice crystal clouds. The heated atmosphere expands according to the ideal gas law, its density decreasing as temperature rises, creating buoyancy forces that drive vertical circulation patterns throughout the atmospheric column. Dust that has rested undisturbed on the Martian surface for decades or centuries suddenly takes flight as the pressure waves sweep across the landscape. The thin atmosphere normally lacks the density to lift particles larger than a few micrometers, but the shock waves from the impacts create pressure differentials and wind velocities capable of raising grain sizes that would remain firmly anchored under normal conditions. Ancient dust deposits accumulated in crater bottoms and valley floors begin to stir, their reddish particles catching the wan sunlight as they spiral upward in convective columns. The planetary boundary layer, that thin interface between Mars's surface and its free atmosphere, becomes a roiling mass of turbulent motion as thermal energy from the impacts disrupts the normally stable stratification of atmospheric density. Temperature inversions that typically cap vertical air movement dissolve under the assault of rising thermals, allowing dust and vapor to reach altitudes normally forbidden by atmospheric stability. The boundary layer expands from its typical height of a few kilometers to encompass nearly the entire troposphere, fundamentally altering the planet's vertical atmospheric structure. Mars possesses a global circulation system driven by solar heating and the planet's rotation, a simplified version of Earth's atmospheric dynamics operating under conditions of extreme aridity and low pressure. The impact-generated disturbances inject massive amounts of energy into this circulation system, perturbing wind patterns that normally follow predictable seasonal cycles. The planet's atmospheric dynamics respond to this energy input like a complex fluid mechanical system suddenly forced far from equilibrium, generating cascading effects that will propagate through the circulation patterns for months. The Coriolis effect, arising from Mars's rotation, begins to influence the expanding dust clouds as they reach sufficient size and duration to fill the planet's 24-hour and 37-minute rotational period. Dust particles lifted into the atmosphere follow curved trajectories that deflect to the right in the northern hemisphere and to the left in the southern hemisphere. The same geophysical force that shapes weather patterns on Earth, but operating under the unique conditions of Mars's thinner atmosphere and different rotational characteristics. Atmospheric scientists have observed that Martian dust storms can grow from localized disturbances to planet-wide phenomena through positive feedback mechanisms that involve radiative heating and atmospheric dynamics. Dust particles absorb solar radiation more efficiently than the surrounding atmosphere, heating the air and creating additional thermal updrafts that lift more dust into suspension. The impact-generated dust clouds possess initial energy levels that far exceed those of normal dust storm initiation, virtually guaranteeing that the disturbances will evolve into major atmospheric events. The mystery of dust storm evolution on Mars lies partly in the complex interactions between particle size distributions, atmospheric stability, and radiative transfer processes. Computer models struggle to predict which local dust storms will evolve into regional or global events, as the nonlinear dynamics involved make the system extremely sensitive to initial conditions. The current impact-generated disturbances represent controlled experiments in dust storm initiation, providing data that may improve understanding of these poorly understood atmospheric phenomena. Only took 4 billion years of atmospheric evolution to create the precise conditions necessary for these dust storms to develop a delicate balance of atmospheric pressure, surface composition, and thermal structure that allows fine particles to remain suspended for extended periods. Mars's thin atmosphere occupies a narrow range of pressure and density values that permit dust transport without the overwhelming turbulence that would characterize similar processes under Earth's denser, atmospheric conditions. The towering dust columns rising from the impact sites begin to interact with Mars's sparse hydrological cycle as they encounter regions of atmospheric water vapor. The combination of dust particles and water vapor creates conditions favorable for the formation of ice crystal clouds, similar to the processes that generate terrestrial cirrus clouds, but operating under the extreme cold and aridity of the Martian atmosphere. These hybrid dust-ice clouds possess optical properties that affect the planet's radiative balance, altering the distribution of solar heating and contributing to atmospheric temperature variations. Electrostatic forces generated by friction between dust particles create electrical fields within the expanding dust clouds, a phenomenon observed in terrestrial dust storms and volcanic eruptions, but operating under the unique conditions of Mars's thin atmosphere and low humidity. These electrical effects can generate radio emissions detectable by sensitive receivers, creating electromagnetic signatures that mark the passage of dust storms across the planet's surface. The impact-generated storms carry enough energy to produce electrical phenomena of unprecedented intensity in the Martian atmosphere. The planet's two small moons, Phobos and Deimos, orbit within the upper reaches of Mars's extended atmosphere. Their surface is constantly bombarded by atmospheric molecules and dust particles carried aloft by various circulation processes. The current dust storms will eventually loft particles to altitudes that intersect the Moon's orbital paths, contributing additional material to the slow erosion processes that gradually alter their surface compositions. This represents another pathway by which impact events influence the broader Martian system beyond the planet's surface and atmosphere. Seasonal variations in atmospheric circulation patterns normally confine large-scale dust storms to specific times of the Martian year. Typically during southern hemisphere summer, when increased solar heating creates the thermal gradients necessary to drive global atmospheric motion, the impact-generated disturbances occur outside this normal seasonal cycle, creating atmospheric conditions that may persist longer than typical dust storms due to the absence of the seasonal forcing mechanisms that usually dissipate such events. The expanding dust clouds begin to interact with topographic features across Mars's varied landscape, flowing around and over mountain ranges, through valley systems, and across vast plains with fluid dynamics that follow principles similar to terrestrial atmospheric flow patterns. The planet's extreme topographic relief, including features like Olympus Mons that rises 24 kilometers above the surrounding plains, creates complex wind patterns and circulation cells that will influence the ultimate distribution of impact-generated dust across the planetary surface. Infrared radiation from the heated dust clouds begins to alter the planet's thermal balance as particles absorb solar energy during the day and radiate heat back to space during the night. This process creates temperature variations that drive additional atmospheric motion, sustaining the dust storms through radiative feedback mechanisms that can maintain atmospheric disturbances for weeks or months after the initial energy input. The dust clouds effectively transform Mars into a more efficient absorber of solar radiation, temporarily warming the planet's surface through increased atmospheric capacity. The polar regions of Mars exist in a state of perpetual transition, their ice caps advancing and retreating with the rhythm of the planet's seasons like vast glacial breathing systems responding to the subtle variations in solar energy that drive Martian climate. The northern polar cap consists primarily of water ice, overlain by seasonal deposits of frozen carbon dioxide, while the southern cap maintains a permanent layer of carbon dioxide ice that never completely sublimes even during the warmest summer temperatures. These polar reservoirs contain the majority of Mars's atmospheric mass in frozen form, cycling between solid and gaseous phases according to orbital mechanics and seasonal heating patterns that have operated with clockwork precision for billions of years. Water vapor released from the sublimating asteroids begins its journey toward the polar regions almost immediately upon entering the atmosphere, carried by global circulation patterns that transport moisture from equatorial regions toward the planet's frozen caps. The thin Martian atmosphere can hold only minute quantities of water vapor before reaching saturation, particularly at the extremely low temperatures that characterize polar regions during winter months. The newly added moisture represents a temporary but significant increase in the atmospheric water budget, equivalent to several % of the total water vapor normally present in the entire planetary atmosphere. The transport of water vapor through Mars's atmosphere follows circulation patterns driven by the planet's rotation and the differential heating between equatorial and polar regions. These atmospheric rivers operate according to fluid dynamic principles that scale across planetary atmospheres, from the massive cyclonic systems of Jupiter to the delicate moisture transport processes of Mars's gossamer atmospheric envelope. The vapor molecules follow three-dimensional pathways that curve and spiral under the influence of Coriolis forces, their trajectories mapped by computer models that track individual parcels of air as they move through the planet's circulation system. As water vapor encounters the increasingly frigid conditions near Mars's polar regions, it begins to condense onto microscopic dust particles suspended in the atmosphere, forming ice crystal clouds at altitudes where temperatures drop below the frost point. These polar clouds contribute to complex radiative feedback processes that influence the planet's climate system through their effects on atmospheric heating and cooling. The clouds absorb and scatter solar radiation during polar summer months, while radiating thermal energy back to space during the long polar winter, creating seasonal variations in the energy balance of the polar atmosphere. The northern polar cap experiences dramatic seasonal changes as spring warming causes the overlying carbon dioxide frost to sublimate, revealing the underlying water ice that persists throughout the Martian year. This seasonal CO2 sublimation releases enormous quantities of gas into the atmosphere, increasing global atmospheric pressure by roughly 25% as the frozen cap returns to vapor form. The newly arrived water vapor will participate in these seasonal cycles, contributing to the complex interplay between solid and gaseous phases that characterizes Martian polar meteorology. Atmospheric models predict that the impact-derived water vapor will require several Earth years to complete its initial mixing throughout the planet's atmosphere before reaching equilibrium concentrations at the polar caps. During this transport phase, the vapor will participate in cloud formation processes at various latitudes and altitudes, contributing to the formation of ice crystal clouds that occasionally produce the only precipitation observed on Mars. These clouds rarely produce precipitation that reaches the surface due to the extreme aridity of the lower atmosphere, but they play important roles in atmospheric radiative transfer and temperature regulation. The mystery of water transport to Mars's polar regions involves complex interactions between atmospheric dynamics, surface topography, and seasonal radiative forcing that researchers are only beginning to understand. Why do the polar caps maintain their current sizes and compositions, rather than growing or shrinking over geological timescales? The balance between water vapor transport toward the poles and sublimation losses back to the atmosphere represents a delicate equilibrium that has apparently remained stable for millions of years despite ongoing atmospheric loss processes. The southern polar region receives less water vapor transport than its northern counterpart due to atmospheric circulation patterns influenced by the planet's topographic asymmetry and orbital characteristics. Mars's elliptical orbit causes southern hemisphere summers to coincide with the planet's closest approach to the Sun, creating more extreme seasonal temperature variations in the south than in the north. Only took 4 billion years of atmospheric evolution to establish these circulation patterns, transport systems fine-tuned by the patient grinding of seasonal cycles, repeated billions of times. The deposition of new water vapor at the polar caps occurs through processes that operate on molecular scales, but accumulate over vast areas and extended time periods. Individual water molecules condense onto ice crystal surfaces through van der Waals forces and hydrogen bonding, the same intermolecular attractions that give water its unique properties throughout the solar system. These molecular scale processes aggregate into macroscopic ice accumulation that gradually adds mass to the polar caps at rates measured in micrometers per year under normal conditions. Layered deposits within the polar caps preserve records of atmospheric composition and climate variations stretching back millions of years. Similar to ice core records from terrestrial glaciers, but operating under the unique conditions of Mars's thin atmosphere and extreme seasonal temperature variations. Each annual layer contains trapped atmospheric gases, dust particles, and isotopic signatures that reveal information about past climate states. The newly deposited water vapor will eventually become part of this geological record, preserving evidence of the asteroid impact event in ice layers that may persist for millions of years. The polar regions also serve as cold traps that can sequester atmospheric water vapor for extended periods, effectively removing moisture from the active atmospheric cycle. During winter months, when polar temperatures drop below -100 degrees Celsius, virtually all atmospheric water vapor that encounters the polar atmosphere condenses immediately onto surface ice or suspended ice crystals. This process helps regulate the planet's atmospheric water content, preventing the accumulation of water vapor beyond the low concentrations observed today. Sublimation processes at the polar caps operate according to temperature-dependent vapor-pressure relationships that create seasonal feedback mechanisms in the Martian climate system. When polar temperatures rise during summer months, increased sublimation rates release water vapor back to the atmosphere, while cooling during winter months causes net condensation and ice accumulation. The newly added water vapor will participate in these seasonal oscillations, contributing to the complex mass balance that determines the long-term stability of the polar ice reserves. The interaction between polar ice and atmospheric dust creates unique geological processes that have no direct analogues on Earth. Dust storms occasionally deposit layers of fine particles onto the polar ice surfaces, creating distinct stratigraphic markers that help scientists interpret the chronology of polar ice accumulation. The current impact-generated dust storms will likely contribute such marker horizons to the polar ice record, preserving evidence of the asteroid impact event in sedimentary layers that may remain visible for thousands of years. Orbital variations in Mars's axial tilt and eccentricity create long-term climate cycles that influence the stability and size of the polar ice caps over timescales of hundreds of thousands of years. These Milankovitch cycles drive periodic changes in the distribution of solar energy across the planet's surface, alternately favouring ice accumulation at one pole versus the other. The current epoch represents one phase in these cyclical variations, with the polar caps existing in configurations that reflect the present orbital parameters and may change significantly as Mars's orbital characteristics evolve over geological timescales. The newly arrived water vapor molecules carry isotopic signatures that will become permanently incorporated into the polar ice record once they condense and accumulate in the ice caps. These isotopic ratios differ from those of existing Martian water reservoirs, providing future investigators with chemical evidence of the asteroid impact event encoded in the molecular structure of polar ice. The preservation of such isotopic signatures demonstrates the remarkable fidelity with which ice can maintain chemical information over geological timescales, creating natural archives of planetary history written in crystalline water. Deep beneath Mars's rust-coloured surface, seismic energy from the twin impacts begins its journey through the planet's interior structure, like ripples spreading through a cosmic pond made of stone and metal. The shock waves generated by the collisions propagate outward from the impact sites at velocities determined by the elastic properties of Martian rock, travelling fastest through the dense basaltic materials of the crust, and slowing as they encounter boundaries between different geological layers. These seismic waves carry with them information about both the impacts that created them and the internal structure of the planet through which they travel, encoding data about Mars's composition, density, and thermal state in their arrival times and amplitude patterns. Primary waves, or P waves, race ahead of the slower-moving secondary waves through the planet's interior, compressing and expanding the rock through which they pass like acoustic pulses transmitted through solid media. These compression waves achieve velocities of roughly 8 km per second in the Martian mantle, allowing them to traverse the planet's diameter in less than 20 minutes. Behind them follow the S waves, shear waves that oscillate perpendicular to their direction of travel and cannot propagate through liquid materials, making them sensitive probes of the physical state of Mars's interior layers. The planet's internal structure reveals itself through the behaviour of these seismic waves as they encounter boundaries between the crust, mantle, and core regions. Mars possesses a layered internal architecture similar to Earth's, with a thin basaltic crust overlying a rocky mantle composed primarily of iron and magnesium silicate minerals. At the planet's centre lies a metallic core of iron-nickel alloy. Though whether this core remains partially molten or has completely solidified remains one of the outstanding mysteries of Martian planetary science. Seismic monitoring stations scattered across Mars's surface detect the arriving waves with sensitive instruments capable of measuring ground motions smaller than the diameter of atomic nuclei. These seismometers operate on the same principles as their terrestrial counterparts, but must function under the extreme environmental conditions of the Martian surface, where temperatures can vary by over 100 degrees Celsius between day and night. The instruments record not only the direct waves from the impact sites, but also reflected and refracted waves that have bounced off internal boundaries or travelled along curved paths through the planet's interior. The timing of seismic wave arrivals at different monitoring stations allows scientists to triangulate the precise locations of the impact sites and calculate the magnitude of energy released during the collisions. This process follows the same principles used to locate earthquakes on our own planet, but the sparse network of seismic stations on Mars requires sophisticated computational techniques to extract maximum information from limited data sets. Each seismometer provides a unique perspective on the waves passing beneath it, contributing pieces to a planetary puzzle that reveals Mars's hidden internal architecture. The amplitude and frequency content of the seismic waves carry information about the physical properties of the materials through which they have travelled, allowing researchers to infer the density, elasticity, and temperature of rocks at various depths within the planet. High-frequency waves attenuate more rapidly than low-frequency waves as they propagate through rock, creating characteristic spectral signatures that reveal information about the internal friction and thermal state of Martian materials. These seismic signatures provide the only direct method available for studying the deep interior of Mars, regions forever hidden beneath thousands of kilometers of overlying rock. Mars's seismic activity under normal conditions remains relatively quiet compared to Earth's tectonically active surface, with most detected earthquakes or Marsquakes originating from thermal stresses created by daily temperature cycling, rather than from active plate tectonics. The planet lacks the vigorous convective processes that drive terrestrial plate motions. Having cooled sufficiently over billions of years to develop a thick, rigid lithosphere that rarely experiences significant tectonic deformation. The impact-generated seismic waves represent some of the largest artificial seismic events ever recorded on Mars, providing unprecedented opportunities to study the planet's internal structure. The mystery of Mars's internal heat sources involves complex interactions between radioactive decay, primordial heat from planetary accretion, and heat transport processes that operate over geological timescales. Unlike Earth, which maintains active volcanism and plate tectonics through vigorous internal convection, Mars appears to have entered a phase of geological quiescence where internal heat generation barely exceeds heat loss to space. Only took 4 billion years for Mars to cool from a molten state to its current thermally subdued condition, a cooling process that determined the planet's current geological character and habitability potential. The propagation of seismic waves through Mars's interior follows principles of wave physics that remain constant whether applied to sound waves in air or seismic waves in planetary materials. The waves experience reflection, refraction, and diffraction at boundaries between materials with different physical properties, creating complex wave patterns that require sophisticated analysis techniques to interpret. Computer models simulate wave propagation through hypothetical internal structures, allowing scientists to test different models of Martian composition against the observed seismic data. Surface waves, which travel along the planet's surface rather than through its interior, create the rolling motions that cause the most obvious surface effects during large seismic events. These waves possess lower frequencies than body waves, and can maintain significant amplitudes over vast distances, potentially causing detectable ground motion thousands of kilometers from the impact sites. The interaction of surface waves with Mars's varied topography creates complex interference patterns that influence the distribution of seismic energy across the planet's surface. The planet's core structure remains one of the most poorly constrained aspects of Martian internal architecture, with fundamental questions about its size, composition, and physical state still awaiting definitive answers. Seismic waves that travel through the core region experience different velocities and attenuation characteristics depending on whether the core material exists in solid or liquid form. The current impacts provide powerful seismic sources that may finally resolve questions about core properties that have puzzled planetary scientists since the first spacecraft began studying Mars from orbit. Resonant frequencies within Mars's interior create standing wave patterns that can amplify certain seismic signals while suppressing others, similar to the acoustic resonances that determine the tonal qualities of musical instruments. The planet's spherical geometry and layered internal structure support various normal modes of oscillation that become excited during large seismic events. These free oscillations continue long after the initial seismic waves have passed, causing the entire planet to ring like a cosmic bell struck by the asteroid impacts. The seismic energy dissipated by the impacts represents only a tiny fraction of the total kinetic energy carried by the asteroids before collision, yet this energy proves sufficient to generate detectable ground motions across the entire planet. The efficiency of converting impact energy to seismic waves depends on factors including impact velocity, target material properties, and crater formation processes that operate during the first seconds following collision. Most of the impact energy goes into heating, vaporizing, and excavating target materials, with seismic wave generation representing a secondary effect of the crater formation process. Atmospheric coupling between seismic waves and the thin Martian atmosphere creates additional complexity in seismic signal interpretation, as pressure waves generated by ground motion can propagate through the atmosphere and return to the surface at distant locations. These atmospheric phases arrive at seismic stations with characteristic timing and amplitude signatures that must be distinguished from direct seismic waves travelling through the solid planet. The coupling between solid Earth and atmospheric motion provides additional constraints on both seismic source properties and atmospheric structure. The long-term effects of the impact-generated seismic activity may include the triggering of secondary Mars quakes as stored tectonic stress finds release through fault systems weakened by the passage of seismic waves. This phenomenon, known as dynamic triggering, has been observed following large earthquakes on our own planet, and may operate similarly in the Martian environment. The impacts thus serve as natural experiments in planetary seismology, providing insights into both immediate impact effects and longer-term geological responses to sudden energy injection into planetary systems. The Martian regolith, that ancient blanket of dust and weathered rock that mantles the planet's surface, undergoes instantaneous transformation as the tremendous heat and pressure generated by the asteroid impacts sweep across the landscape in expanding circles of molecular reorganization. This surface layer, accumulated over billions of years through the patient grinding of meteorite bombardment, thermal cycling, and wind erosion, contains iron-bearing minerals that have oxidized under the planet's thin atmosphere to create the characteristic rust-red coloration that gives Mars its distinctive appearance from space. Now, in the span of microseconds, chemical bonds that have remained stable for geological epochs break and reform under conditions that briefly recreate the interior temperatures of stars. Iron oxides, hematite, magnetite, and the various forms of rust that coat nearly every grain of Martian dust experience phase, transitions that transform their crystal structures and magnetic properties under the extreme pressures propagating outward from the impact sites. The shock metamorphism process operates according to thermodynamic principles that remain constant, whether applied to laboratory samples under controlled conditions or to planetary surfaces subjected to cosmic bombardment. Pressures exceeding 100 gigapascals compress the crystal lattices of common minerals into dense, high-pressure polymorphs that can only form under such extreme conditions. The heat generated by shockwave compression raises temperatures high enough to melt and vaporize surface materials, creating microscopic beads of glass from what moments before existed as crystalline mineral grains. This impact glass preserves within its frozen structure the chemical composition of the original minerals, while recording the extreme conditions of its formation through distinctive textures and trace element distributions. The glass formation process occurs so rapidly that there is insufficient time for crystal nucleation and growth, trapping the molten material in an amorphous state that will persist for millions of years. Silicate minerals within the regolith undergo structural transformations that create new mineral phases rarely observed in terrestrial rocks. Plagioclase feldspar converts to mascaleinite, a dense glass form that retains the original mineral's composition while adopting a completely different internal structure. Olivine and pyroxene, the dominant minerals in Martian basaltic rocks, transform into high-pressure phases with increased density and altered optical properties. These mineralogical changes serve as permanent markers of impact processes, preserved evidence that will allow future investigators to identify and study impact-affected materials. The chemistry of impact metamorphism involves more than simple heating and compression, as the extreme conditions promote chemical reactions that would be impossible under normal planetary surface conditions. Sulfur-bearing minerals, common in Martian regolith due to the planet's volcanic history and atmospheric composition, undergo reduction reactions that release sulfur dioxide and hydrogen sulfide gases into the expanding vapor clouds. These volatile sulfur compounds contribute distinctive odors and chemical signatures to the impact plumes, adding complexity to the atmospheric chemistry modifications triggered by the collisions. Organic compounds, if they exist within the impact-affected regolith, face destruction or synthesis depending on the specific pressure and temperature conditions they encounter. The extreme energy densities generated during impact can break down complex organic molecules into simpler components, while simultaneously creating conditions favourable for the formation of new organic compounds through shock synthesis reactions. This dual nature of impact chemistry, both destructive and creative, plays important roles in the evolution of organic matter on planetary surfaces throughout the solar system. The magnetic properties of iron-bearing minerals change dramatically during shock metamorphism, as crystal structures reorganize and magnetic domains realign under extreme stress. Magnetite, which normally exhibits strong magnetic properties, may convert to weakly magnetic hematite or lose its magnetic characteristics entirely through thermal demagnetization. These changes in magnetic mineralogy affect the local magnetic field signatures recorded in the regolith, creating magnetic anomalies that will persist long after the impacts and serve as geological markers of the collision events. Water molecules adsorbed onto mineral grain surfaces or trapped within crystal structures undergo rapid dehydration as shock heating drives off volatiles at temperatures exceeding several hundred degrees Celsius. This process releases additional water vapor to supplement the sublimation occurring within the asteroids themselves, contributing to the total atmospheric water budget increase resulting from the impacts. The dehydration reactions follow kinetic pathways that depend on mineral composition and structure, with hydrated sulfate minerals losing water more readily than silicate phases. The mysterious behavior of Martian regolith under extreme shock conditions reveals itself through comparison with laboratory experiments conducted using high-velocity impact devices and diamond anvil cells that can recreate the pressures and temperatures of asteroid collisions. These controlled experiments demonstrate that many common Martian minerals undergo multiple phase transitions as pressure increases, creating complex sequences of mineralogical changes that depend on the precise shock conditions experienced during impact events. Only took 4 billion years of surface weathering to create the perfect mineral assemblage for these shock metamorphism experiments, a natural laboratory prepared by geological processes and activated by cosmic collisions. The formation of shock veins and melt pockets within the regolith creates heterogeneous zones where different minerals experience varying degrees of metamorphism depending on their distance from fracture surfaces and their thermal conductivity properties. These microscopic variations in shock effects preserve detailed information about the pressure and temperature gradients that existed during the brief moments of impact heating. The resulting textures resemble those observed in shocked meteorites found on Earth, providing terrestrial analogues for understanding Martian impact processes. Chemical diffusion processes, normally negligible at typical planetary surface temperatures, become significant during the brief periods of extreme heating that accompany shock metamorphism. Elements migrate between adjacent mineral grains, creating compositional gradients and reaction zones that record the thermal history of impact-affected materials. These diffusion profiles can be analysed using sophisticated microanalytical techniques to determine the peak temperatures and cooling rates experienced during shock events. The interaction between shock waves and the heterogeneous structure of Martian regolith creates complex patterns of deformation and metamorphism that vary on microscopic scales. Porous regions of the regolith experience different shock effects than dense, consolidated areas, leading to patchy distributions of metamorphic effects that reflect the original structure of the pre-impact surface materials. This heterogeneity and shock metamorphism creates sampling opportunities for future missions, as different degrees of shock effects may be preserved within individual samples. Trace element chemistry provides additional insights into the shock metamorphism processes as volatile elements are selectively lost during heating, while refractory elements become concentrated in residual phases. The partition coefficients that govern element distribution between different mineral phases change dramatically at high temperatures, causing redistribution of trace elements that can be detected through sensitive analytical techniques. These chemical fingerprints of shock metamorphism persist long after the impacts, creating permanent records of the extreme conditions that briefly transformed ordinary regolith into exotic high-pressure mineral assemblages. The crystallographic defects created by shock deformation dislocations, planar fractures, and amorphous domains within otherwise crystalline minerals serve as microscopic strain gauges that record the magnitude of stress experienced during impact events. These defect structures can be observed using transmission electron microscopy and other advanced characterization techniques, providing quantitative measures of the shock pressures and strain rates that operated during the collisions. The preservation of such microscopic evidence demonstrates the remarkable ability of mineral structures to record and maintain information about transient extreme events. The electromagnetic environment surrounding Mars transforms as charged particles from the solar wind encounter the expanding clouds of ionized gas and metallic debris created by the asteroid impacts, generating auroral displays that paint ghostly curtains of light across the planet's star-filled night sky. Unlike Earth's robust magnetic field, which creates a well-defined magnetosphere capable of deflecting most solar wind particles, Mars possesses only remnant magnetic fields embedded in its ancient crustal rocks, like fossilized memories of a planetary dynamo that ceased operating billions of years ago. These scattered magnetic anomalies, strongest in the southern hemisphere's heavily cratered terrain, create a complex patchwork of magnetic field lines that interact with solar wind plasma in ways fundamentally different from the orderly magnetic field geometry that protects our own planet. The solar wind, that perpetual stream of charged particles flowing outward from the sun's corona, normally interacts directly with Mars's upper atmosphere due to the absence of a global magnetic field barrier. Protons and electrons accelerated to velocities exceeding 400 km per second penetrate deep into the Martian magnetosphere, where they collide with atmospheric molecules and gradually strip away the planet's thin envelope of gas through a process known as atmospheric sputtering. The impact-generated plasma clouds temporarily alter this interaction by creating localized regions of enhanced magnetic field strength and electrical conductivity that deflect and channel incoming solar wind particles. The collision between solar wind plasma and the ionized debris from the asteroid impacts creates shock fronts in the electromagnetic field configuration surrounding Mars, temporary boundaries where the kinetic energy of charged particle streams converts to electromagnetic energy through plasma physics processes that operate according to magnetohydrodynamic principles. These shock structures accelerate electrons and ions to energies sufficient to excite atmospheric molecules when they eventually collide with the planet's upper atmosphere, creating the characteristic emission lines that produce auroral light in the thin Martian air. Atmospheric molecules excited by high-energy particle collisions emit photons at wavelengths determined by their electronic structure and energy level transitions, creating spectral signatures that reveal the composition and physical conditions of the upper atmosphere. Oxygen atoms, dissociated from carbon dioxide by ultraviolet radiation, emit green light at 558 nanometers when electrons cascade from excited states back to lower energy levels. Carbon dioxide molecules contribute blue and ultraviolet emissions through vibrational and electronic transitions, while trace amounts of water vapor and other atmospheric constituents add their own characteristic colors to the auroral palette. The magnetic field lines embedded in Mars's crust channel charge particles along curved trajectories that concentrate auroral activity over specific geographic regions, creating localized light displays that correspond to the locations of the strongest crustal magnetic anomalies. These magnetic field configurations resemble Earth's polar auroral zones, but operate on much smaller spatial scales, creating multiple discrete auroral regions scattered across the planet's surface, rather than the continuous oval patterns characteristic of terrestrial auroral displays. The impact-generated disturbances enhance these natural auroral processes by injecting additional energetic particles into the magnetospheric system. The mystery of Martian auroral processes involves the complex interaction between multiple magnetic field sources, crustal magnetic anomalies, induced magnetic fields created by atmospheric electrical currents, and the interplanetary magnetic field carried by the solar wind. These field systems interact non-linearly, creating magnetic reconnection events where field lines break and reconnect with explosive releases of stored magnetic energy. The asteroid impacts temporarily enhance these processes by creating additional sources of ionized plasma that participate in the electromagnetic interactions occurring in Mars's extended magnetosphere. Radio emissions generated by the accelerated charged particles propagate through the Martian magnetosphere and interplanetary space at the speed of light, creating electromagnetic signals that can be detected by sensitive receivers on spacecraft throughout the solar system. These radio signatures provide remote sensing capabilities for studying the electromagnetic effects of the impacts, as the frequency and intensity characteristics of the emissions reveal information about the particle energies and magnetic field strengths involved in the auroral processes. Only took 4 billion years of magnetic field evolution to create the precise conditions necessary for these exotic electromagnetic phenomena, a planetary laboratory for studying plasma physics under conditions impossible to replicate on Earth. The interaction between magnetic fields and electrically conducting plasma follows the fundamental equations of magnetohydrodynamics, mathematical relationships that describe how magnetic fields and fluid motion couple in ionized gases. The plasma generated by the asteroid impacts possesses electrical conductivity that allows it to carry electrical currents, which in turn create magnetic fields according to Ampere's law. These induced magnetic fields interact with existing magnetic field structures to create complex field geometries that evolve dynamically as the plasma expands and cools following the initial impact events. Electrical currents flowing through the impact-generated plasma create Joule heating effects that maintain elevated temperatures in the ionized gas long after the initial shock heating has dissipated. This process operates like a cosmic electric heater, converting electromagnetic energy into thermal energy through the resistance of the plasma to electrical current flow. The sustained heating helps maintain the ionization state of the expanding gas clouds, prolonging the electromagnetic effects of the impacts and extending the duration of enhanced auroral activity around Mars. The propagation of electromagnetic waves through the Martian magnetosphere follows dispersion relationships that depend on the plasma density and magnetic field strength encountered along the wave path. Different wave modes, Alphen waves, magnetosonic waves, and electromagnetic ion cyclotron waves propagate at different velocities and undergo different interactions with the plasma medium. These wave phenomena create complex interference patterns and resonance effects that influence the efficiency of particle acceleration and energy transport processes within the magnetosphere. Particle precipitation into Mars's atmosphere occurs when magnetic field lines connect the regions of enhanced particle acceleration to the atmospheric boundary, allowing energetic electrons and ions to follow magnetic field lines down into the upper atmosphere where they collide with neutral molecules. The precipitation patterns depend on the detailed magnetic field topology, which varies significantly across Mars's surface due to the heterogeneous distribution of crustal magnetic sources. The impact events temporarily modify these precipitation patterns by altering the magnetic field configuration through plasma dynamic effects. The temporal evolution of the electromagnetic disturbances follows characteristic timescales determined by the physical processes governing plasma dynamics and magnetic field diffusion. Initial electromagnetic effects occur within seconds of the impacts as shock waves propagate through the plasma medium, while longer-term effects persist for hours or days as magnetic field lines gradually relax to new equilibrium configurations. The decay of electromagnetic activity depends on plasma cooling rates, magnetic field dissipation processes, and the continued influence of solar-wind interactions. Spectroscopic observations of the enhanced auroral displays reveal information about atmospheric composition and temperature structure in Mars's upper atmosphere, regions normally difficult to study due to their extreme altitude and tenuous density. The excitation cross-sections for different atmospheric molecules vary with particle energy, creating auroral intensity patterns that depend on both the atmospheric composition and the energy spectrum of precipitating particles. These natural experiments in atmospheric physics provide unique opportunities to study processes that operate continuously but at much lower intensities under normal conditions. The electromagnetic signature of the asteroid impacts propagates outward through interplanetary space as radio waves and plasma disturbances that will eventually reach other planets and spacecraft throughout the solar system. These travelling disturbances carry information about the impact events encoded in their frequency spectrum and polarization characteristics, creating natural transmissions that reveal details about both the impacts themselves and the electromagnetic properties of the interplanetary medium through which they propagate. The impacts thus serve as natural experiments in space physics, generating controlled disturbances that can be studied throughout the solar system using multiple observation platforms. Deep beneath Mars's surface, in pockets and caverns carved by ancient volcanic activity and sealed by geological processes that operated billions of years ago, methane gas rests in patient darkness like a chemical time capsule waiting for release. These subsurface reservoirs formed through complex geochemical processes that remain poorly understood, perhaps through the thermal decomposition of organic compounds buried in early Martian sediments, or through serpentinization reactions between water and iron-rich minerals in the planet's crust, or through biological processes that operated during Mars's more clement past, when liquid water flowed across its surface. The methane molecules trapped in these underground chambers carry within their molecular structure potential clues to some of the most profound questions in planetary science, whether life ever existed on Mars, and whether it might exist there still. The shockwaves generated by the asteroid impacts propagate through Mars's crustal rocks like seismic hammers striking the planet's subsurface architecture, creating fracture networks that breach the integrity of sealed chambers and provide pathways for trapped gases to escape toward the surface. The brittle rocks overlying methane reservoirs yield to the passage of seismic energy, developing cracks and fissures that serve as conduits connecting previously isolated gas pockets to the planet's atmospheric system. This process operates according to fracture mechanics, principles that govern rock failure under stress, with the magnitude and direction of fracturing determined by the local stress field and the mechanical properties of different rock types. Methane release from subsurface sources follows pressure-driven flow through the newly created fracture networks, with gas migration rates controlled by the permeability of fractured rock and the pressure differential between underground reservoirs and the low-pressure Martian atmosphere. The gas ascends through the regolith like an invisible geological exhale, carrying with it isotopic signatures that preserve information about its origin and formation processes. The molecular composition of released methane includes not only the primary CH4 molecules, but also trace amounts of higher hydrocarbons and other organic compounds that provide additional clues about subsurface chemistry. The atmospheric detection of methane on Mars has puzzled scientists for decades, Due to the apparent mismatch between methane production rates inferred from atmospheric measurements and the gas's short lifetime in the oxidizing Martian atmosphere. Ultraviolet radiation from the sun photodissociates methane molecules in the upper atmosphere within a few hundred years, while chemical reactions with hydrogen peroxide and other oxidants in the lower atmosphere provide additional destruction mechanisms. The persistence of methane in atmospheric measurements thus requires continuous or episodic replenishment from subsurface sources, making the impact-triggered release events potentially significant contributors to the planet's atmospheric methane budget. Orbital spacecraft equipped with sensitive spectrometers have detected methane concentrations that vary both spatially and temporally across Mars's surface, with some regions showing persistent methane emissions while others remain apparently methane-free. These observations suggest a complex pattern of subsurface source regions and atmospheric transport processes that create the observed distribution patterns. The impact-generated fracturing may activate previously dormant source regions, creating new methane emission sites that will contribute to the planet's atmospheric inventory for years or decades following the collision events. The mystery of Martian methane extends beyond simple detection to questions about its ultimate origin and the processes responsible for its formation and storage. On Earth, the vast majority of atmospheric methane originates from biological processes, leading to speculation that Martian methane might similarly indicate the presence of life in the planet's subsurface environment. However, several abiotic processes can also produce methane under the appropriate chemical conditions, including serpentinization reactions between water and ultramafic rocks that have been proposed as potential sources for Martian methane emissions. Serpentinization chemistry operates through the reaction of water with iron-bearing silicate minerals to produce hydrogen gas, which can subsequently react with carbon dioxide or carbon-bearing minerals to form methane through Fischer-Tropsch type synthesis reactions. These processes require specific temperature and pressure conditions that may exist in Mars's deep crustal environment, where geothermal gradients and confining pressures create chemical reaction zones capable of producing organic compounds through purely geological processes. Only took 4 billion years of crustal evolution to establish the precise conditions necessary for these methane formation processes. Subsurface chemical factories operating in the planet's hidden depths. The isotopic composition of released methane provides crucial information for distinguishing between biological and geological formation mechanisms, as different processes create characteristic ratios of carbon-12 to carbon-13 that serve as chemical fingerprints. Biological methane production typically favors the lighter carbon-12 isotope, creating methane with distinctive isotopic signatures that differ from thermogenic or abiotic methane formation processes. The isotopic analysis of impact-release methane may finally resolve questions about the ultimate source of Martian atmospheric methane that have remained unanswered despite years of telescopic and spacecraft observations. The subsurface migration of methane through fractured rock follows principles of reservoir geology that govern hydrocarbon accumulation and migration on Earth. But operating under the unique conditions of Mars's low gravity and atmospheric pressure, gas migration rates depend on factors including fracture connectivity, rock permeability, and pressure gradients that drive flow from high-pressure reservoirs toward the low-pressure surface environment. The impact-generated fractures create new migration pathways that may drain methane reservoirs that have remained isolated for millions of years. Atmospheric chemistry models predict that the newly released methane will undergo photochemical reactions with other atmospheric constituents, creating complex reaction networks that produce secondary organic compounds and influence the overall atmospheric composition. These photochemical processes operate according to reaction kinetics that depend on temperature, pressure, and the availability of reactant molecules, creating seasonal and diurnal variations in atmospheric chemistry that can be detected through spectroscopic observations from orbiting spacecraft. The temporal evolution of methane emissions from impact-generated fractures depends on the healing and closure of fractures through secondary mineralization processes that gradually reduce rock permeability over time. Mineral precipitation from groundwater circulation can seal fractures within years to decades, creating transient windows of enhanced methane release that may explain some of the temporal variability observed in Martian atmospheric methane concentrations. The impacts thus serve as natural experiments in subsurface gas release, providing insights into the mechanisms that control methane emissions under Martian conditions. Trace gas chemistry in Mars's atmosphere involves complex interactions between methane, water vapour, carbon dioxide, and other minor atmospheric constituents that create reaction pathways leading to the formation of organic hazes and aerosol particles. These secondary organic compounds may contribute to atmospheric opacity and climate effects, while providing additional chemical signatures that can be detected through atmospheric observations. The enhanced methane release triggered by the impacts will participate in these atmospheric chemistry processes, potentially creating detectable changes in atmospheric composition that persist long after the initial emission events. The distribution of subsurface methane sources across Mars's surface remains poorly constrained due to the difficulty of detecting and mapping underground gas reservoirs from orbital observations. The impact-generated fracturing provides a natural sampling mechanism that may reveal the locations and characteristics of previously unknown methane reservoirs, creating opportunities for comparative studies of subsurface chemistry in different geological terrains. These natural experiments in subsurface gas release offer unique insights into the three-dimensional distribution of organic compounds within Mars's crust. The Martian wind begins its patient work on the freshly excavated crater walls almost immediately after the violence of impact subsides, carrying microscopic grains of pulverized rock across the landscape with the same inexorable persistence that has sculpted the planet's surface features for billions of years. This atmospheric erosion operates under the unique conditions of Mars's thin atmosphere, where wind velocities must exceed threshold values nearly 10 times higher than those on Earth to lift particles of equivalent size due to the reduced atmospheric density at the planet's surface. Yet despite these constraints, the Martian atmosphere possesses sufficient energy to transport vast quantities of dust across continental distances, creating the global dust storms that periodically shroud the entire planet in reddish haze. The fresh crater rims rise above the surrounding terrain like newly born mountain ranges, their steep slopes unstable under the relentless pull of Martian gravity and the thermal stresses created by daily temperature cycling that can exceed 100 degrees Celsius between day and night. These extreme temperature variations cause repeated expansion and contraction of surface materials according to the thermal expansion coefficients of different mineral phases, creating mechanical stresses that gradually weaken rock structure and promote the formation of fractures along grain boundaries and crystal defects. The process operates like a cosmic freeze-thaw cycle, but instead of water expansion driving the mechanical weathering, thermal expansion and contraction of silicate minerals provides the energy for gradual rock breakdown. Atmospheric pressure variations associated with seasonal changes in Mars's carbon dioxide ice caps create additional stress cycles that contribute to mechanical weathering processes through pressure-induced volume changes in porous rock materials. As atmospheric pressure oscillates by roughly 25% between winter and summer due to the sublimation and condensation of polar carbon dioxide, rocks experience cyclic loading and unloading that promotes fatigue, failure, and grain boundary weakening over thousands of seasonal cycles. These barometric pressure changes operate on much longer timescales than daily thermal cycling, but contribute cumulative damage that accelerates the overall weathering process. The crater walls exhibit steep angles of repose that represent temporary equilibrium between gravitational forces pulling material downward and the cohesive forces holding rock fragments in place on near vertical slopes. This equilibrium remains delicately balanced, with small perturbations from wind loading, thermal expansion, or seismic vibrations capable of triggering mass-wasting events that redistribute material from crater rims toward crater floors. The angle of repose for loose material under Martian gravity conditions differs from terrestrial values due to the reduced gravitational acceleration, allowing steeper, stable slopes than would be possible under Earth's stronger gravitational field. Chemical weathering processes operate slowly in Mars's arid environment, where liquid water exists only under the most favourable temperature and pressure conditions, and then only for brief periods during the warmest parts of summer days. However, even trace amounts of atmospheric water vapour can participate in chemical reactions when it condenses onto mineral surfaces during the cold Martian nights, creating thin films of liquid water that promote dissolution and precipitation reactions at the molecular scale. These chemical processes follow thermodynamic principles that remain constant whether operating in terrestrial soils or on the surface of distant planets, but the reaction rates depend critically on temperature, water activity, and the availability of reactive mineral phases. The mystery of long-term erosion rates on Mars involves the complex interplay between mechanical and chemical weathering processes operating under conditions that have no direct analogues in terrestrial environments. How rapidly do crater walls retreat under the combined influence of wind erosion, thermal cycling, and chemical alteration? Crater counting studies suggest that Martian erosion rates average several orders of magnitude lower than typical terrestrial rates, reflecting both the reduced atmospheric density and the scarcity of liquid water that drives rapid chemical weathering in Earth's more clement environment. Saltation processes, where sand-sized particles bounce across the surface in arcing trajectories driven by wind shear, create abrasion effects that gradually wear down rock surfaces through countless microscopic impacts. Each grain collision removes nanoscopic amounts of material through mechanical abrasion. Following wear laws that relate material loss rates to particle size, impact velocity, and target material properties, only took 4 billion years of atmospheric circulation to establish the wind patterns and particle transport mechanisms that now begin their slow work of erasing the fresh impact craters, a testament to the patient persistence of atmospheric processes operating over geological timescales. The distribution of wind-transported sediment follows atmospheric circulation patterns that concentrate dust in specific geographic regions according to seasonal pressure gradients and topographic influences on airflow. Large impact craters act as dust traps that collect wind-blown particles in their floors, while simultaneously serving as sediment sources through the erosion of their walls and rim deposits. This dual role creates complex sediment budgets, where material eroded from crater walls accumulates in crater floors before potentially being redistributed by subsequent dust storm events. Aeolian erosion patterns develop through the selective removal of less resistant minerals and rock fragments, creating differential erosion surfaces that reflect the mechanical properties of different geological materials. Softer minerals and highly fractured rocks erode preferentially, while more resistant faces like quartz and heavy minerals concentrate as lag deposits on eroded surfaces. These selective erosion processes create surface textures and mineral concentrations that preserve information about both the original impact processes and the subsequent weathering history. The formation of ventifex wine-sculpted rocks with distinctive streamlined shapes and polished surfaces proceeds through abrasion processes that operate according to fluid dynamic principles governing particle-surface interactions in turbulent airflow. The characteristic shapes of ventifex reflect the dominant wind directions and velocities that have operated over the timescales required for their formation, typically thousands to millions of years depending on rock hardness and atmospheric conditions. The fresh impact craters will eventually develop ventifex populations that record the local wind climate during their erosional evolution. Dust devil activity. Those small-scale atmospheric vortices that frequently traverse Mars's surface during periods of strong thermal convection contributes additional erosional energy through the enhanced wind velocities and particle loading that characterize these rotating dust columns. Individual dust devils can achieve wind speeds exceeding 30 meters per second, sufficient to lift sand-sized particles and transport them across considerable distances. The statistical frequency of dust devil encounters with specific surface locations determines their contribution to long-term erosion rates through cumulative effects of repeated erosional episodes. Chemical alteration of freshly exposed crater wall materials begins immediately upon exposure to the Martian atmosphere, as reactive mineral surfaces interact with atmospheric gases and trace amounts of water vapor, Iron-bearing minerals undergo oxidation reactions that produce the characteristic rust-red coloration of Martian dust, while sulfate and chloride salts form through reactions between volcanic gases and atmospheric constituents. These chemical weathering processes operate slowly but continuously, gradually transforming the mineralogy of surface materials and contributing to the chemical evolution of Martian soils. The preservation potential of impact crater morphology depends on the balance between crater formation rates and erosion rates operating over geological timescales, with well-preserved craters indicating either recent formation or particularly resistant target materials and favourable preservation conditions. Statistical studies of crater size frequency distributions across different terrains reveal information about both the impact history and erosion rates, characteristic of different Martian surface units, allowing researchers to calibrate erosion models using the natural experiments provided by impact crater populations. Regolith development within and around the fresh craters will proceed through the gradual accumulation of wind-blown dust and locally derived rock fragments created by ongoing weathering processes. This regolith formation represents the initial stages of soil development, albeit under the unique conditions of Mars's thin atmosphere and extreme aridity. The physical and chemical properties of developing regolith depend on the composition of source materials, weathering processes, and dust accumulation rates that vary significantly across different regions of Mars's surface due to variations in climate, geology, and topographic setting. Fragments scattered by the primary collisions drift in lazy arcs around Mars, like a temporary asteroid belt hugging close to the planet's surface. Their trajectory is governed by the same orbital mechanics that guide moons and spacecraft, but operating on much smaller scales and shorter timescales. These debris clouds consist of material excavated from the impact craters mixed with fragments of the original asteroids, creating a heterogeneous collection of rock, metal, and ice particles ranging in size from microscopic dust grains to house-sized boulders that tumble slowly end over end as they follow ballistic paths through the thin Martian atmosphere. The largest fragments achieve sufficient velocity during excavation to briefly achieve orbital trajectories, while smaller particles follow shorter parabolic arcs that return them to the surface within minutes or hours of their violent ejection from the crater sites. The physics of ejector emplacement follows ballistic trajectory calculations that must account for Mars's reduced surface gravity, atmospheric drag effects, and the planet's rotation during the flight time of projectiles launched at various angles and velocities. Material ejected at angles less than 45 degrees from horizontal achieves maximum range under ideal conditions, though atmospheric drag and the irregular shapes of rock fragments create complex aerodynamic effects that modify the theoretical trajectories predicted by simple ballistic equations. The reduced gravitational acceleration on Mars, roughly 38% of Earth's surface gravity, allows ejector to travel much farther from impact sites than would be possible under terrestrial conditions, creating debris fields that extend hundreds of kilometers from the primary craters. The ejector velocity distribution reflects the shockwave attenuation characteristics within the target materials, with the highest velocity fragments originating from regions near the impact points, where shock pressures exceeded the material strength of bedrock by the largest margins. These fastest-moving fragments carry sufficient kinetic energy to excavate secondary craters when they eventually return to the surface, creating chains and clusters of smaller impact structures that radiate outward from the primary impact sites, like cosmic shrapnel patterns frozen in stone. The secondary crater formation process operates according to the same physical principles as primary impacts, but at reduced scale due to the lower velocities and smaller masses of the projectiles involved. Some fragments follow trajectories that carry them completely around Mars before returning to impact the surface on the opposite side of the planet, creating antipodal effects similar to those observed on other heavily cratered worlds throughout the solar system. These circumplanetary trajectories require precise combinations of ejection angle and velocity to maintain sufficient altitude to avoid atmospheric drag while possessing enough energy to complete nearly complete orbits around the planet. The mathematical requirements for such trajectories represent special cases in orbital mechanics, where the projectile's ballistic path intersects the planet's surface after travelling distances comparable to Mars's circumference. The temporary debris clouds interact with Mars's thin atmosphere through drag forces that selectively remove smaller particles, while allowing larger fragments to maintain their orbital or ballistic trajectories for extended periods. Atmospheric drag effects scale with the surface area to mass ratio of individual particles, causing dust-sized grains to decelerate rapidly, while boulder-sized fragments experience negligible atmospheric resistance during their flight through the tenuous Martian air. This size-dependent separation process creates sorting effects that influence the spatial distribution of different particle size classes across the ejector fields surrounding the impact sites. The mystery of long-range ejector transport involves the complex interactions between impact physics, atmospheric dynamics, and orbital mechanics that determine the ultimate fate of material excavated during large impact events. Why do some fragments achieve stable temporary orbits, while others follow direct ballistic trajectories to immediate surface impact? This sensitive dependence of trajectory outcomes on initial conditions creates chaotic dynamics where small differences in ejection, angle, or velocity can lead to dramatically different final destinations for otherwise similar fragments. Orbital decay processes gradually remove debris from temporary orbits around Mars as atmospheric drag, solar radiation pressure, and gravitational perturbations from Mars's moons combine to lower orbital altitudes until atmospheric re-entry becomes inevitable. The timescales for orbital decay depend on the initial orbital altitude and the atmospheric drag coefficient of individual fragments, with some debris potentially remaining in orbit for weeks or months before eventually returning to the surface. Only took 4 billion years of impact crater formation to establish the orbital dynamics and atmospheric conditions that now govern the fate of freshly ejected material natural experiments in planetary debris transport operating under well-defined physical constraints. The larger fragments that survive atmospheric re-entry create secondary impact events distributed across Mars's surface, according to statistical patterns that reflect the physics of the original excavation process and the subsequent orbital evolution of the debris clouds. These secondary impacts occur randomly in time and space as individual fragments complete their orbital or ballistic trajectories, creating a temporally extended impact event that may continue for days or weeks after the initial asteroid collisions. Each secondary impact represents a scaled-down version of the original event, complete with its own shockwave generation, crater excavation, and ejector production. The composition of orbital debris reflects the heterogeneous nature of both the impacting asteroids and the Martian target materials, creating a natural sampling experiment that redistributes geological materials across the planet's surface. Fragments of ancient Martian bedrock ejected from deep within the impact craters carry with them isotopic and chemical signatures that preserve information about Mars's early geological history, while asteroid fragments contribute exotic materials with chemical compositions that differ markedly from typical Martian surface rocks. This mixing process creates natural meteorite falls that deposit extraterrestrial materials across Mars's surface. Impact crater chains formed by the sequential impact of fragment trains create distinctive geological features that preserve information about the original debris trajectories and the timing of secondary impact events. These crater chains typically align with the orbital mechanics of the debris clouds, creating linear patterns that point back toward the primary impact sites and preserve information about the initial ejector velocity vectors. The morphology and spacing of craters within these chains provide constraints on the original fragment sizes and velocities that can be compared with theoretical predictions from impact modeling studies. The interaction between orbital debris and Mars's two small moons creates additional complexity in the trajectory evolution of the largest ejector fragments, as gravitational encounters with Phobos and Deimos can alter orbital elements and create resonance effects that influence long-term orbital stability. These gravitational perturbations operate on timescales comparable to the orbital periods of the moons themselves, creating periodic variations in debris trajectories that depend on the relative orbital phases of the moons and the debris particles. Such three-body gravitational interactions represent classical problems in celestial mechanics, scaled down to the environment of a single planet and its debris clouds. The thermal evolution of orbital debris follows heating and cooling cycles, determined by solar illumination geometry and radiative heat loss to space, creating temperature variations that can cause thermal stress fracturing and further fragmentation of the large debris pieces. The extreme temperature variations experienced during orbital flight, from direct solar heating to shadowed cooling in Mars's orbital environment, subject rock fragments to thermal cycling effects that promote mechanical weathering and size reduction through repeated expansion and contraction cycles. Spectroscopic observations of orbital debris provide opportunities for remote compositional analysis of materials excavated from depths within Mars's crust that would otherwise be inaccessible to surface-based or orbital investigations. The debris clouds serve as natural sampling missions that bring subsurface geological materials into orbital environments where they can be studied using sophisticated remote sensing techniques. These observations reveal information about the three-dimensional distribution of different rock types within Mars's crust, and the extent of chemical differentiation that has occurred during the planet's geological evolution. The electromagnetic properties of metallic debris fragments create radar signatures that can be detected by ground-penetrating radar systems and orbital radar instruments, providing additional means for tracking and characterizing the orbital debris population. Iron-rich fragments from the asteroid cores and metallic phases within Martian target rocks exhibit distinctive electromagnetic scattering properties that differ from the silicate-rich materials that comprise the majority of the debris clouds. These electromagnetic signatures persist long after the debris returns to the surface, creating detectable anomalies in subsurface radar surveys. The Martian day begins with temperatures so cold that carbon dioxide sublimates directly from the atmosphere onto exposed rock surfaces, creating microscopic frost patterns that disappear within hours as the weak but persistent sunlight warms the planet's rust-coloured landscape. This daily thermal cycling subjects the newly fractured crater walls to mechanical stresses that exceed the elastic limits of most common minerals, creating conditions where repeated expansion and contraction gradually propagate existing fractures deeper into the bedrock through a process that operates like geological fatigue failure. The temperature differential between the shadowed and sunlit portions of crater walls can exceed 50 degrees Celsius within minutes of sunrise, generating thermal gradients steep enough to create significant differential expansion between adjacent rock layers. The coefficient of thermal expansion varies among different mineral phases according to their crystal structure and chemical bonding characteristics, with some minerals expanding nearly twice as much as others under identical temperature changes. This differential expansion creates internal stresses within heterogeneous rocks composed of multiple mineral phases, gradually weakening grain boundaries and crystal interfaces through countless cycles of thermal loading and unloading. Quartz grains expand differently than feldspar crystals, while iron-bearing minerals exhibit thermal expansion coefficients that differ from their silicate matrix, creating microscopic stress concentrations that accumulate damage over thousands of thermal cycles. The propagation of thermal fractures follows principles of fracture mechanics that describe how cracks grow under cyclic loading conditions, with each thermal cycle contributing a small increment of crack extension that gradually compromises the structural integrity of rock masses. Stress intensity factors at crack tips reach critical values when thermal stresses exceed the fracture toughness of specific mineral phases, causing sudden crack propagation events that can extend fractures by millimeters or centimeters in single thermal cycles. These fracture propagation events release stored elastic energy with audible acoustic emissions, creating the thermal cracking sounds that characterize rapid temperature changes in rocky environments. The newly exposed surfaces created by impact excavation possess higher surface area to volume ratios than weathered rock surfaces, making them particularly susceptible to thermal stress effects due to their greater exposure to direct solar radiation and radiative cooling to space. Fresh fracture surfaces exhibit sharp edges and unweathered mineral faces that absorb and emit thermal radiation more efficiently than dust-coated weathered surfaces, creating enhanced thermal cycling effects that accelerate the initial stages of mechanical weathering in recently formed craters. The absence of protective dust coatings on fresh rock surfaces eliminates the insulating effects that normally moderate thermal cycling in older geological features. Martian atmospheric pressure variations create additional cyclic loading effects that complement thermal stresses in promoting fracture growth and rock breakdown processes. The thin Martian atmosphere exerts pressures equivalent to only about 1% of Earth's sea level atmospheric pressure. But even these modest pressure variations create measurable volume changes in porous rocks and contribute to fatigue loading effects when combined with thermal cycling. The elastic modulus of fractured rock decreases as crack density increases, making progressively more weathered materials increasingly susceptible to both thermal and pressure-induced deformation. The mystery of thermal weathering rates under Martian conditions involves the complex interactions between mineral properties, fracture geometry, and environmental loading cycles that determine how rapidly fresh rock surfaces deteriorate under the planet's extreme thermal environment. Laboratory studies of thermal cycling effects on terrestrial rocks provide insights into the fundamental processes, but the unique combination of temperature ranges, atmospheric conditions, and mineral assemblages found on Mars creates weathering environments that have no direct terrestrial analogues. Only took 4 billion years of thermal cycling to establish the equilibrium between rock formation and weathering processes that maintains Mars's current surface texture, a balance disrupted by the fresh exposure of unweathered materials in the impact craters. The formation of thermal contraction polygons in fine-grained surface materials creates distinctive geometric patterns that reflect the interplay between thermal stresses and the mechanical properties of regolith and bedrock. These polygonal crack networks develop when thermal contraction stresses exceed the tensile strength of surface materials, creating systematic fracture patterns that minimize the total elastic strain energy in the contracting material. The polygon's size and shape depend on material properties, thermal cycling magnitude, and the boundary conditions imposed by underlying bedrock or the geometry of surface topography. Sublimation and condensation cycles of atmospheric water vapor contribute additional weathering effects, as trace amounts of moisture undergo phase transitions on mineral surfaces during daily temperature oscillations. Water molecules adsorbed onto mineral surfaces during cold nighttime periods can participate in hydrolysis reactions that gradually alter mineral compositions, while sublimation during daytime heating creates volume changes that contribute mechanical stress to existing fracture systems. These hydration-dehydration cycles operate at the molecular scale, but accumulate measurable effects over thousands of daily cycles. The anisotropic thermal properties of many common minerals create preferential fracture orientations that depend on crystal structure and the direction of heat flow through the material. Mica and other layered silicate minerals exhibit thermal expansion coefficients that vary significantly with crystallographic direction, causing thermal stresses to concentrate along specific crystal planes and creating systematic fracture patterns that reflect the underlying mineral fabric. These structurally controlled fracture systems create weakness planes that influence the long-term erosional evolution of crater walls and other geological features. Rock breakdown products generated by thermal cycling contribute to regolith development through the gradual accumulation of mineral fragments and altered surface materials around the fresh crater sites. The size distribution of thermal weathering products depends on the original rock texture, mineral grain size, and fracture spacing, with coarse-grained igneous rocks typically producing larger fragments than fine-grained sedimentary or volcanic materials. These weathering products provide source materials for wind transport and dust storm development, contributing to the global atmospheric dust loading that characterizes Mars's climate system. The heat capacity and thermal conductivity of different rock types create variations in thermal cycling response that depend on mineralogy, porosity, and moisture content of surface materials. Dense, low-porosity rocks conduct heat more efficiently than porous materials, creating different temperature gradients and thermal stress distributions during daily heating and cooling cycles Vesicular basalts and other volcanic rocks with high porosity exhibit different thermal weathering characteristics than dense crystalline rocks, leading to terrain-dependent variations in weathering rates and surface texture development. Infrared thermal emission from heated rock surfaces follows Stefan Boltzmann relationships that create nonlinear temperature dependencies in radiative heat loss rates, with small increases in surface temperature producing disproportionately large increases in thermal radiation to space. This nonlinear thermal response creates complex feedback relationships between surface heating, thermal emission, and the magnitude of thermal cycling effects that depend on the specific temperature ranges experienced at different latitudes and seasons on Mars. The thermal emission characteristics also influence atmospheric heating through absorption of infrared radiation by atmospheric dust and trace gases. The development of exfoliation features curved fracture surfaces that parallel exposed rock faces represents a long-term response to repeated thermal cycling that creates onion skin weathering patterns in massive rock formations. These exfoliation processes operate through stress release mechanisms as thermal expansion and contraction gradually propagate fractures parallel to free surfaces, eventually creating curved fracture planes that follow the topographic contours of exposed rock faces. The spacing and curvature of exfoliation fractures depend on rock properties, thermal cycling magnitude, and the geometry of the exposed surfaces. Frost wedging effects, though limited by Mars's arid conditions, can occur during the brief periods when atmospheric water vapor condenses and later sublimes in rock fractures during daily temperature cycles. The 9% volume expansion that accompanies the phase transition from liquid water to ice creates significant mechanical forces in confined spaces, though the rarity of liquid water on Mars limits the extent of traditional frost wedging processes. However, similar effects can occur with carbon dioxide frost, which forms more readily under Martian conditions and undergoes significant volume changes during sublimation. Mars receives these cosmic gifts with the same patient silence that has characterized its existence for billions of years, absorbing the asteroid materials into its geological record, like a planetary librarian carefully cataloguing new acquisitions in an archive that spans the entire history of the solar system. The impact-generated debris, the sublimated water vapor, the pulverized rock fragments, and the complex chemical signatures created during the collisions will all become part of the stratified narrative written in sedimentary layers, mineral deposits, and atmospheric compositions that future investigators may one day decipher. Every grain of dust disturbed by the impacts carries within its crystalline structure information about both the cosmic visitors and the planetary processes that welcome them, creating microscopic time capsules that preserve evidence of this brief but violent encounter between Mars and its ancient guests from the outer solar system. The geological timescale on which these impacts will be recorded and preserved operates according to principles of stratigraphy that treat each depositional event as a page in an ever-growing book of planetary history. The dust clouds settling from the impact-generated atmospheric disturbances will create distinct sedimentary horizons in accumulating deposits across Mars's surface, markers that will remain visible in geological cross-sections for millions of years to come. These impact signatures will join the countless other thin layers that record volcanic eruptions, dust storms, climate variations, and other episodic events in Mars's past, contributing to the complex stratigraphic sequences that preserve information about 4 billion years of planetary evolution. The isotopic signatures embedded in the asteroid materials, the distinctive ratios of heavy to light elements that reveal their origins in the cold outer reaches of the solar system, will become permanently incorporated into Mars's geochemical inventory through weathering, erosion, and sedimentary processes. Water molecules with their characteristic deuterium ratios will mix with existing Martian water reserves, creating subtle but measurable changes in isotopic compositions that could theoretically be detected by sensitive analytical instruments thousands of years in the future. The organic compounds released during impact heating will contribute to the planet's inventory of complex carbon chemistry, adding molecular diversity to chemical reservoirs that may have remained unchanged for eons. Deep time operates on Mars through the same geological processes that shape terrestrial landscapes, but at rates modified by the planet's unique environmental conditions and reduced atmospheric density. Crater walls that appear fresh and sharply defined today will gradually soften and retreat under the influence of wind erosion, thermal cycling, and rare episodes of mass wasting triggered by seismic events or meteorite impacts. The steep slopes created by excavation will slowly approach angles of repose determined by the mechanical properties of Martian regolith and the planet's reduced surface gravity, eventually creating crater morphologies that reflect millions of years of gradual modification rather than the violence of their formation. The atmospheric water vapor added by sublimating asteroid ice will participate in Mars's hydrological cycle for as long as atmospheric loss processes permit its retention. Contributing molecules to polar ice caps, atmospheric humidity, and the trace amounts of water vapor that occasionally condense into ice crystal clouds. Some water molecules may become incorporated into hydrated mineral phases through slow chemical weathering reactions, creating permanent chemical reservoirs that preserve the water in crystalline form for geological ages. Others will eventually escape to space through photodissociation processes in the upper atmosphere, their hydrogen atoms joining the steady stream of atmospheric constituents that Mars has been losing to space for billions of years. The mystery of geological preservation on Mars involves the complex interplay between deposition and erosion processes that determine which events become permanently recorded in the stratigraphic sequence and which disappear without trace through subsequent weathering and erosion. The planet's thin atmosphere and reduced weathering rates favour preservation compared to Earth's more aggressive erosional environment. Yet even on Mars, the geological record remains incomplete, with gaps and unconformities that represent missing intervals of time when erosion exceeded deposition. Only took 4 billion years to create the preservation conditions that will now archive evidence of these cosmic collisions in sedimentary sequences that may persist until the Sun evolves beyond its current stable state. The three-dimensional distribution of impact effects throughout Mars's crustal structure creates a complex pattern of chemical and physical modifications that extend far beyond the visible crater boundaries. Shock metamorphism effects penetrate into the subsurface along fracture networks and through the propagation of pressure waves, altering mineral compositions and creating new chemical phases at depths measured in kilometers rather than meters. These subsurface modifications represent permanent changes to Mars's internal structure that will influence groundwater flow, seismic wave propagation, and heat transfer processes for millions of years. Sedimentary processes will gradually redistribute impact-generated materials across Mars's surface through wind transport, mass wasting, and the rare episodes of liquid water flow that may occur under favourable temperature and pressure conditions. The finest dust particles will travel thousands of kilometres from their source regions, contributing to global atmospheric dust loading and eventually settling in depositional environments where they become incorporated into growing sedimentary sequences. Coarser fragments will migrate shorter distances but still contribute to regional sedimentary budgets through processes that operate over thousands to millions of years. The electromagnetic signatures created by the impact's radio emissions, auroral displays, and temporary modifications to Mars's magnetospheric environment represent transient phenomena that will fade within days or weeks as plasma clouds dissipate and electromagnetic field configurations return to pre-impact states. Yet even these ephemeral effects may leave permanent traces in the form of induced magnetization in iron-bearing minerals exposed to enhanced magnetic fields during the electromagnetic disturbances. These paleomagnetic signatures could theoretically preserve directional information about the impact-generated magnetic fields in rock samples for millions of years. Chemical weathering products created through the interaction of impact-generated materials with Mars's atmosphere and surface environment will contribute to the planet's evolving soil chemistry through slow but persistent alteration processes. Sulfate minerals, chloride salts, and iron oxides formed through atmospheric chemical reactions will accumulate in surface deposits and contribute to the complex chemical signatures that characterize different regions of Mars's surface. These chemical modifications represent permanent additions to Mars's geochemical inventory that will influence future chemical evolution through their effects on mineral stability and reaction pathways. The biological implications of the impact events, if any exist, will depend on whether Mars harbours subsurface microbial communities that could benefit from the temporary injection of water, organic compounds, and other potentially life-supporting materials delivered by the asteroids. The subsurface fracturing created by seismic waves may provide new pathways for groundwater circulation and nutrient transport, potentially creating habitat opportunities in previously isolated subsurface environments. However, these biological effects, if they occur at all, will likely remain undetectable without direct subsurface exploration using sophisticated life detection instruments. The statistical significance of these impact events within the broader context of Mars's bombardment history represents a continuation of processes that have operated throughout the solar system's existence. From the heavy bombardment of the first billion years to the sporadic impacts that continue today, each impact contributes to the cumulative modification of planetary surfaces through crater formation, ejecta emplacement, and atmospheric interactions that gradually alter planetary environments over geological timescales. These events serve as reminders of the dynamic nature of the solar system and the ongoing exchange of materials between different planetary environments. The preservation of impact evidence in Mars's geological record will depend on the balance between deposition and erosion that characterizes different surface environments, with some regions favoring long-term preservation, while others experience rapid erasure of geological features through active erosional processes. The impact signatures will become part of the complex stratigraphic archive that records Mars's environmental history, joining evidence of ancient river systems, lake deposits, volcanic eruptions, and climate variations in the layered sequences that preserve information about planetary evolution over deep time. The ultimate fate of the impact-generated materials will be determined by the same geological processes that have shaped Mars's surface for billions of years: wind erosion, thermal cycling, chemical weathering, and the gradual redistribution of surface materials through atmospheric and gravitational processes. Some materials will become permanently incorporated into sedimentary sequences, while others will continue to circulate through surface and atmospheric reservoirs until eventual loss to space through atmospheric escape processes. The impacts thus represent both an ending and a beginning, marking the conclusion of the asteroid's 4 billion-year journey while initiating new chapters in the ongoing geological story of Mars. The Martian night settles over the impact sites with the profound stillness that has characterized countless evenings on the red planet for billions of years, its thin atmosphere offering little resistance to the radiative heat loss that drops surface temperatures to levels where carbon dioxide begins to condense as frost on the newly excavated crater walls. The craters rest in darkness now, their fresh scars invisible beneath a canopy of stars that shine with crystalline clarity through an atmosphere too thin to blur their ancient light. In this cosmic quiet, the violence of the day's collisions seems as distant as the formation of the planets themselves, absorbed into the patient geological rhythms that measure time in millions of years rather than heartbeats. Dust motes suspended in the cooling air begin their slow descent back to the surface, each grain carrying within its microscopic structure the chemical memory of shock waves and plasma formation, of ancient ice transformed to vapour and bedrock, fractured by forces that briefly rivaled the interior of stars. These particles will settle into the growing sedimentary archive that preserves Mars's history in layers of accumulated dust and debris, adding new pages to a story that began when the solar system was young and will continue long after the sun exhausts its nuclear fuel and expands into a red giant that may finally warm Mars to temperatures suitable for liquid water. The seismic waves generated by the impacts continue to propagate through Mars's interior, growing fainter with each passage but still carrying information about the planet's internal structure toward a seismic monitoring station scattered across the surface. In the deep silence of Martian caves and subsurface chambers, these acoustic whispers represent some of the few sounds that disturb the absolute quiet of a world without weather as we know it. without the constant susurrus of wind through leaves or the splash of waves against shores. Above the settling dust, the planet's thin atmosphere gradually returns to its normal state of near equilibrium with the surface, its enhanced water vapour content beginning the slow process of transport toward polar regions, where much of it will eventually condense into the ice caps that have waxed and waned with seasonal rhythms for millions of years. The methane molecules released from subsurface reservoirs drift through this tenuous air mass like chemical messengers carrying information about Mars's hidden interior, their isotopic signatures preserving clues about geological processes that may have operated in the planet's warmer, wetter past. In the profound stillness of this alien evening, Mars continues its ancient orbital dance around the Sun with the same mathematical precision that has governed planetary motion since the solar system achieved its current configuration. The red planet turns on its axis with metronomic regularity, bringing new regions of its surface into the pale sunlight of dawn, while others slip into the star-filled darkness of night. Time flows differently here, measured not in minutes or hours, but in the slow accumulation of geological changes that reshape planetary surfaces over eons of patient transformation. The impact craters, fresh and sharp-edged now, begin their long journey toward the rounded, dust-filled depressions they will become after millions of years of wind erosion and thermal cycling have softened their profiles and filled their depths with accumulated sediment. This transformation will occur so slowly as to be imperceptible on human timescales, yet with the inexorable certainty of geological processes that operate according to physical laws as fundamental as gravity itself. The craters join the countless other circular scars that dot Mars's ancient surface, each one a frozen moment of cosmic violence now at peace in the planetary stillness. The silence deepens as Mars rotates away from the impact sites, carrying them into the shadow of night where temperatures drop toward the frost point and the thin atmosphere radiates its modest heat content back to space. In this crystalline cold, water vapour begins to condense onto dust particles and rock surfaces, creating microscopic ice deposits that will sublimate again when dawn returns, but for now add their small contribution to the planet's endless cycle of deposition and erosion. The asteroid materials, scattered and transformed by the violence of impact, rest quietly in their new geological contexts, becoming part of Mars itself through the alchemy of collision and time. Stars wheel overhead in patterns unchanged since the impacts began, their light crossing interplanetary space to illuminate a world where the cosmic violence of asteroid collision has given way to the deeper peace of geological time. The red planet sleeps beneath this starlight, absorbing its cosmic gifts into the sedimentary archive that preserves the history of the solar system in layers of accumulated dust and stone, where future explorers may one day discover evidence of this day when Mars received visitors from the cold outer darkness and welcomed them home with the patient grace of deep time itself.